Hello my dear students, welcome to IMS GATE Academy. I hope all of you attended our quick revision session of digital circuit subject earlier. Those who couldn't attended that session, you can watch that session in your free time. So in this particular session, we are going to discuss regarding communication system subject, the entire formulas for all the chapters. Okay, so this subject is common for two branches, EC and instrumentation. So all of you kindly share this video link with all of your friends so that they also will attend this session in live and they also will get benefited from this session. Yeah, very good evening one and all. So in this particular subject, communications, we are having total 6 chapters. So the first chapter is Introduction to Communication System and Amplitude Modulation. And then second chapter, angle modulation. Third chapter, AM and FM receivers. Fourth chapter, random process and noise. Fifth chapter, digital communication. And sixth chapter, information theory. Here all the chapters belongs to EC branch with respect to GATE syllabus. Okay, only the chapter 4 is not there for instrumentation. Chapter 4 is not there for instrumentation. And chapter 6 also is not there for instrumentation. Okay, so all the 6 chapters is the part of the GATE syllabus for EC branch, whereas for instrumentation, except 4th chapter and 6th chapter, the remaining all the chapters are part of the GATE syllabus. So coming to the weightage, so for EC branch, the weightage will be 8 to 12 marks, whereas for instrumentation, the weightage will be 3 to 5 marks. Okay, so I am welcoming all of you for this live session. So I hope all of you are eagerly waiting for the session. So let us start. So all of you keep the heading, first chapter, that is Introduction and Amplitude Modulation. Chapter 1, Introduction to Communication System. Introduction to Communication System and Amplitude Modulation. Yeah, good evening Raviteja. Yeah, very good evening one and all. So communication is nothing but what? Transferring or conveying the information from one place to another place, right? So you can say from transmitter to receiver, or you can say source to destination. Okay, we are transferring the information, right? So if I am talking only in the space in a room, okay, if suppose 30 to 40 students are there, whatever I am speaking, all the students can listen. But suppose if the room capacity is 200 students can occupy or can sit. Whatever I am speaking, whether the last bench student can listen, if there are 200 students in a room, if I am directly speaking from here, whether the last bench student can hear my voice. If not, then what is the device that I have to use so that the last bench student can listen my voice? Yes, obviously, if the room is bigger size, okay, the last bench student cannot listen, right? Yeah, so we have to use one transducer, okay. See here, input is whatever I am speaking, that is the voice or speech, okay. So we will use one transducer. The transducer is nothing but microphone. Okay, so this particular transducer will convert the physical signal into the corresponding electrical signal. So here you will get voice signal. here you will get voice signal. Okay, so this is the transducer we are using at the transmitter. Okay, similarly at the receiver, if you want to listen, okay, the audio signal, there also we will use one transducer. Can you guess what is the name of the transducer that we will use at the receiver, so that you will get the audio output? The input is audio signal. Yes, speaker. Very good, Raviteja. Yes, we will use loudspeaker. So here transducer functionality is it will convert the physical form into the electrical signal or electrical form into the physical signal, right? So at the transmitter we are using one transducer, okay, and at the receiver we are using one transducer. Okay, now whatever the voice signal you are getting here, directly instead of transmitting, we will use one modulator here. The output of this one we will give as input for modulator. And then at the receiver we will use demodulator. So in the channel we will transmit that particular signal. So instead of directly transmitting the output of the transducer directly to the receiver, why we are using modulator? Any guess? What is the need of modulator? Why we are using modulator in the transmitter section, and similarly the reverse function is demodulator that we are using at the receiver? Any guess why we are using modulator at the transmitter section instead of directly sending the voice signal directly? See, if you are directly sending the voice signal, what will happen? Voice signal frequency is how much? 300 Hz to 3500 Hz. 300 Hz to 3500 Hz. Okay. So if you are transmitting the signal, then we require antenna height how much? Lambda equal to C by F. So if you are using, suppose if you consider C is 3 into 10 power 8 meter per second and here 3000 Hz, then you are getting in the order of hundreds of kilometers. The antenna height should be hundreds of kilometers, right? So practically designing such a long antenna is difficult, right? So in order to reduce the height of the antenna or length of the antenna, then we have to increase the frequency. Right? So that's why with the help of modulator, we are increasing or we are changing the low frequency signal into high frequency signal. We are changing the low frequency signal into high frequency signal. So that particular operation is performed by the modulator. Why we require modulator? To reduce the antenna height. I hope it is clear for everyone. Okay. Suppose if you are using in the order of megahertz, so because of that, the antenna height will be reduced when compared to in the order of kilohertz, right? So this is one of the main reason why we are using modulator. And one more important application is, say for example, if you want to transmit 10 signals, right? So if suppose all the signals are voice, that means all those signals will be there in this particular bandwidth, right? Suppose if you want to transmit all those 10 signals, okay, so with the help of modulator, if you are just changing to different frequencies, okay, after that you can transmit. So that means here you can perform multiplexing operation we can perform. Multiplexing means we are using the same channel but for transmitting multiple signals, okay. So these are the two reasons why we are using modulator. So the reverse operation is nothing but demodulator that we will use at the receiver. After that, whatever the electrical signal we are getting, we will convert into physical form. So with the help of other transducer. Okay, right. I hope it is clear for everyone. Amol, Raviteja. Okay, why we are using modulator at the transmitter section. Okay, right. So that means here main important thing, suppose if you are considering voice signal is like message signal or modulating signal M of t. Okay, so the high frequency signal required is C of t. C of t is nothing but carrier signal, right? Carrier signal. So for the timing I am writing carrier signal as C of t equal to AC into cos 2 pi FCT plus phi. Okay, so here you are having AC, this is the amplitude of the carrier signal, and FC is the frequency of the carrier signal, and this is the phase angle of the carrier signal. So when you consider one cos signal or sine signal, okay, so regarding that particular signal you are having three parameters. Okay, one is amplitude, one is frequency, one is phase. Okay, so you can vary the amplitude of the carrier, okay, in accordance with the modulating signal amplitude, or you can vary the frequency of the carrier signal in accordance with the modulating signal amplitude. Similarly, if you can vary the phase angle of the carrier signal in accordance with the amplitude of the modulating signal, right? So in this way, based on the parameter, which parameter of the carrier signal is varying in accordance with the modulating signal, that is nothing but according to the respective modulation you will get. So since you are having three parameters of the carrier signal, so accordingly you will get three modulations, that is amplitude modulation, frequency modulation and phase modulation. Okay, so for the timing let us discuss regarding amplitude modulation and then we'll discuss regarding these two modulations one by one. Okay. So all of you put the heading amplitude modulation. So regarding amplitude modulation, the time domain equation of AM wave will be S of t equal to AC into 1 plus Ka M of t into cos 2 pi FCT. AC into 1 plus Ka into M of t into cos 2 pi FCT. So for the timing I am considering M of t is the message signal, that is nothing but AM cos 2 pi FM into t. AC into 1 plus Ka, M of t I am considering as AM into cos 2 pi FM into t into cos 2 pi FCT. Okay, so here Ka into AM is nothing but modulation index. Ka into AM is nothing but modulation index, 1 plus mu into cos 2 pi FM into t into cos 2 pi FCT into cos 2 pi FCT. So here K is nothing but amplitude sensitivity. K is nothing but amplitude sensitivity. So here if you observe AM is the peak value, so the units will be in the order of volt. Okay, so that means here Ka amplitude sensitivity, the units will be okay. K is the amplitude sensitivity. So here unit you will get in the denominator in the order of volts. In the order of volts you will get, because here AM you are having in the order of volts. Okay, right. So K into AM is nothing but modulation index mu. Okay, so here mu value if you are considering 0, mu value if you are considering 0, then what will happen? Mu value 0 means this entire quantity is 0. Then you are getting simply AC into cos 2 pi FCT, right? So that means whatever the unmodulated carrier, that means initially whatever the carrier signal you are having, suppose if there is no phase angle, then the same carrier signal you are getting. So that means mu equal to 0 is nothing but unmodulated, or there is no modulation happened. unmodulated or no modulated, no modulation. Okay. Suppose if mu is less than 1, if mu is less than 1, then you can say undermodulated, and if mu is greater than 1, then you can say it is overmodulated. Okay, right. So when you draw the timing diagram, you will get the time domain equation you are having regarding AM wave like this. So when you draw the waveform, you will get, suppose if you are observing, you are having cos signal here, but regarding amplitude, it will vary with respect to this one, right? So for the timing, if you consider the maximum value, see when you are having cos signal, this entire quantity is nothing but the peak amplitude, right? So from here you will get two values. One is maximum value you will get, and you will get minimum value regarding the peak amplitude. So here if you observe, you are having cos signal. So regarding cos signal, what is the maximum value and what is the minimum value? Regarding cos signal, what is the maximum and what is the minimum value? Yes, very good, Raviteja, very good. Cos signal maximum value is +1 and minimum value is -1, right? So if you consider cos value as +1, then you will get maximum value as AC into 1 plus mu. Similarly, if you consider this cos signal value as -1, then you will get AC into 1 minus mu. AC into 1 minus mu. Okay. So if you do the simplification, okay, just take the average of these two. Okay. See, just first you perform addition of these two, then mu will get cancelled. That means right hand side you are getting 2 times AC, left hand side you are getting Vmax plus Vmin, right? So if you do the simplification, from there you will get AC is nothing but average of Vmax and Vmin. Average of Vmax and Vmin, which is nothing but AC. AC equal to Vmax plus Vmin divided by 2. Okay. So similarly, you can perform like component dividendo operation. So from there you will get modulation index as Vmax minus Vmin, divided by Vmax plus Vmin. Regarding this derivation part, I have already discussed in the gate score booster session regarding communication system subject. So it is very simple. See, just take the ratio of these two, then right hand side AC will get cancelled. After that, left hand side perform like Vmax minus Vmin, that is in the numerator, divided by Vmax plus Vmin in the denominator. Similarly here on the right hand side, on the numerator just add these two quantities, and denominator, if you are performing here subtraction, here also subtraction. If you are performing here addition, here also addition accordingly. So after that rearrange, from there you will get mu is nothing but Vmax minus Vmin by Vmax plus Vmin. So if you remember these formulas, directly whenever you are having waveform regarding AM, okay, AM if you are having regarding positive peak and positive minimum value, okay. Similarly, you will get negative peak and negative minimum value, okay, in the lower side. Okay, for the timing with the help of positive side, that means upper part, from the help of Vmax and Vmin, you calculate AC and you can calculate modulation index. Okay, from the modulation index, based upon these relations, whether it is 0 or less than 1 or greater than 1, from there you can say whether it is what kind of modulation we are performing, whether we are performing any modulation or not accordingly. Now, so this is the signal you are having. I am copying once again. S of t equal to AC into 1 plus mu cos 2 pi fm into t into cos 2 pi fct. Cos 2 pi fct. So multiply cos 2 pi fct with these two quantities. Okay. So from there you will get AC into cos 2 pi FCT plus AC mu into cos 2 pi FCT into cos 2 pi FM into T. Right. So just observe here, you are having, it is in the form of 2 cos A cos B. Okay, if you multiply and divide with 2, then you are getting 2 cos A cos B. Okay, 2 cos A cos B, I hope all of you know the formula. 2 cos A cos B is nothing but cos sum plus cos difference, right? Cos sum plus cos difference. So AC into cos 2 pi FCT plus AC mu by 2 cos A cos B is nothing but cos sum, that is cos 2 pi into FC plus FM into T, 2 cos A cos B, cos sum plus cos difference. Okay, so this quantity I am multiplying directly for both the values, both the terms, AC mu by 2 into cos of 2 pi into FC minus FM into T. I hope it is clear for everyone. 2 cos A cos B is nothing but cos sum plus cos difference. See, if you observe from the beginning of this particular topic, okay, why we are going for modulation? We are changing the low frequency signal into high frequency, right? So that means obviously the message frequency is smaller when compared to the carrier frequency, right? So FC minus FM you will get positive. Anyway, you are performing cos signal. Cos of minus theta is cos theta only, right? Whether you are getting positive or negative, cos of negative also will become cos of positive only, right? Cos of minus theta is nothing but cos theta. So here I have considered, why I have written FC here, why I have written FM here. It is very simple. When you apply 2 cos A cos B, you will get cos sum plus cos difference. When you are performing cos difference, so you can separate smaller from larger. Okay, right. Now, so whenever you are having cos signal or sine signal, I hope all of you know how to calculate the power. So whenever you are having cos signal or sine signal, so whatever the value you are having here, that is nothing but peak value. Okay, in order to calculate the power, what is the formula you will use in general in the network theory subject? Whenever you are having cos signal or sine signal, okay, I hope all of you studied in your AC circuits. In order to calculate the power, yes, very good, Raviteja, very good. So in general, the formula is VRMS square by R. Okay, so here you can assume for the entire communication system subject, R value you can assume 1. So that means power is nothing but simply VRMS square. VRMS is nothing but Vm by root 2. So when you are performing square, you will get Vm square by 2. Vm square by 2. So that means here the peak value is AC. So that means AC square by 2. Whatever the peak value you are having, just perform square and divide with 2. Simple. Similarly, here you are having this term, perform square and then divide with 2. AC mu by 2 whole square divided by 2. Similarly, here also you are having same quantity. So simply I am multiplying with 2 because you are adding 2 times. So that is nothing but multiply this quantity with 2. Both are same. Now, AC square by 2 plus, here 2 will get cancelled, AC square mu square divided by 2 square is nothing but 4. So from these two you can take AC square by 2 as common into 1 plus mu square by 2. So just now we have told, see, when you are having, forget about those two terms, if you are having only this signal, regarding this signal the power is nothing but AC square by 2, the same quantity we are getting, right? So here if you observe, you are having the frequency component FC. So that means this is the carrier power. This is the carrier power. So this one you can write as PC into 1 plus mu square by 2. PC into 1 plus mu square by 2. Okay. So here if you observe, you are having one frequency FC and here you are having another frequency FC plus FM. Here you are having another frequency FC minus FM. Okay. So that means when you observe this particular AM equation, Okay, for the timing you're having the time domain equation. When you draw the spectrum, you will get the spectral components. Okay, now you can visualize instead of drawing the spectrum itself. Even from the equation you can observe you're having one frequency component Fc, another frequency component Fc plus Fm, another frequency component Fc minus Fm. Okay, so among all the frequencies, which one is the larger and which one is the smaller? You're having three frequency components, out of which one is the larger, which one is the smaller? Yes, very good, Raviteja. Fc plus Fm is the larger, right? Yes. So that means if you want to calculate the bandwidth is nothing but highest frequency minus smallest, right? So among all the frequencies, this is the highest. That means Fc plus Fm minus. Among all, the lowest one is this one. Okay. So Fc minus Fm is the smallest. So here minus Fc plus Fc will get cancelled. Minus of minus is nothing but plus, right? Yes, very good, Raviteja. So Fm plus Fm is nothing but 2Fm. So this is the bandwidth of the AM wave. Okay, whatever the message signal frequency, highest frequency you are having, that frequency you have to multiply with 2. Yes, very good, Rohit, very good. Okay, so bandwidth of the AM signal is nothing but twice of the highest frequency of the modulating signal or message signal. Okay, for the timing I have considered single tone. Single tone means you are having only one frequency. But suppose if you are having multiple frequencies, then among all the frequencies of the modulating signal, whichever is the largest, so accordingly that one you can consider, right? Next, so if you observe this equation, you are having Pt equal to Pc into 1 plus mu square by 2. Okay, right. So in terms of current, if you want to write this equation, you can write in terms of current. If you want, you can write power is nothing but IRMS square into R. Okay, so here also R value you can assume 1. Okay, so from there you will get IT square is equal to IC square into 1 plus mu square by 2. Okay, so this one you can rearrange. IT equal to, if you perform square root on both sides, you will get IT equal to IC into square root of 1 plus mu square by 2. 1 plus mu square by 2. Okay, right. So here this particular whatever the equations you are getting regarding power or regarding current, okay, so those relations will applicable even for multi-tone. Only the difference, instead of mu, there we will consider mu t. So when you are having multiple modulating signals, then accordingly you will get multiple modulation indexes, mu1, mu2, mu3 and so on. Okay, so for multi-tone case, mu t square is nothing but mu1 square plus mu2 square and so on and so on. Okay, so this formula you can use. After that, whatever the mu square value you are getting, you can substitute here. That's all. Okay, for multi-tone. Multi-tone means you are having more than one frequency in the message signal. Okay, single tone means you are having only one frequency. That's all. Regarding bandwidth, when you are having multiple frequencies in the modulated signal, whatever the highest frequency you are having, that one you can consider multiply with 2. Okay, right. Now if you observe, so here you are having one frequency component. This is the carrier. This is the carrier frequency. This is the carrier frequency. And when compared to the carrier frequency, this is the higher. This is the higher, right? And that is towards right hand side. Okay, so you can say this is the upper sideband. This is the upper sideband. Upper sideband frequency component. Similarly, when compared to FC, when you draw the frequency spectrum, I am telling this frequency will come below that of carrier frequency. So that means you can say this one is lower sideband. Okay, right. So that means here total power is nothing but the carrier power plus total sideband power. You are having one upper sideband, one lower sideband. Together you are having two sidebands. So these two sidebands power is nothing but Pc into mu square by 2. Pc into mu square by 2. Right. So now if you observe, whatever the modulating signal you want to transmit to the receiver, we are taking the help of carrier signal. Right? So in order to transmit this particular modulating signal, okay, actually the information is present in the sidebands. Okay, but we are transmitting this much power. Okay, let us calculate the efficiency. Modulation efficiency. Eta equal to sideband power, total sideband power divided by transmitted power. If you want eta in percentage, you can multiply with 100. So sideband power is nothing but Pc into mu square by 2. Divided by Pt is nothing but Pc into 1 plus mu square by 2. So here Pc will get cancelled. Do the simplification. You will get mu square divided by 2 plus mu square into 100. So this is the modulation efficiency. Yes, very good, Rohit. Yeah, all of you please respond. Suppose if mu value is 1. Then eta will be how much? If mu value is 1 by root 2, then eta value will be how much? Similarly, if mu is 1 by 2, then what is modulation efficiency in terms of percentage? Yes, very good, Raviteja. For first case, you will get 33.33. So all of you just do the calculation. It is very simple calculation. Yes, very good, Rohit. Very good. For second case, you will get 20%. And try for last case also. Yes, very good, Rohit. 11.11. So you can round figure it to 11%. Or if you want exact, it will be 11.11. Yes. Yes, very good, Raviteja, Rohit. Yes. So you can remember these simple values. Okay, mu value 1, 33%, 1 by root 2, 20%, 1 by 2, 11%. 11% or 11.11. Similarly, this one is, you can make approximate, it will be 33%. How we can generate an AM signal? By using which modulator we can generate AM signal? Yes, very good, Rohit. By using square law modulator. By using square law modulator, we will get AM signal. The final equation you will get like this. V naught equal to A into AC into 1 plus 2B by A into M of t into cos 2 pi f ct. So now if you compare this equation with the standard equation, so A into AC you can consider as like AC dash, okay, AC dash into 1 plus, so this value is nothing but Ka into M of t into cos 2 pi f ct, right? So this Ka is nothing but amplitude sensitivity. Yes, very good, Rohit. Yes. Next one, demodulation of AM signals. Demodulation of AM signals. So regarding demodulation of AM signals, we are having 3 demodulators. So first one is square law demodulator, second one is envelope detector, and third one is synchronous detector. Okay, so square law demodulator and envelope detector we can use only when the modulation index is less than or equal to 1. If modulation index is less than or equal to 1, then we can use any of the first 2 demodulators. Okay, if mu value is greater than 1, then we can use synchronous detector. Okay, so synchronous detector means what? At the receiver you are using the demodulator. Okay, so there also we are using one carrier signal that is generated by the local oscillator. Okay, so when you are transmitting the AM signal, there also you are having carrier signal, right? Suppose if the carrier signal present in the AM signal and if the carrier signal that you are generating at the receiver, if both are having same phase angle, or you can say there is no phase difference between the carriers of both the signals, right? So then we will say both are synchronous. In that case, you will get output of low pass filter. If there is no phase difference, between the carrier signal of AM signal and carrier signal at the output of the receiver, then in that case you will get AC square M of t by 2. But suppose if there is some phase difference between the carrier which is present in the AM signal and the carrier which you are generating at the receiver, if there is some phase angle, because of that you will get here cos phi. Okay, suppose if phi is 0, if phi equal to 0 degrees, that means that is a case for synchronous, there is no phase difference, right? So in that case, output of low pass filter you will get AC square into M of t divided by 2. Suppose if phase angle is 90 degrees. So all of you please respond, what is the output you are going to get in this case? If there is the phase shift between the carrier of AM signal and carrier which you are generating at the local oscillator or at the receiver. If it is 90 degrees, then what is the output you are going to get? Just substitute. Cos 90 is how much? Cos 90 is 0, right? Yes, very good, Raviteja, very good. Cos 90 is nothing but 0. So that means if there is a phase difference in the carrier signal, okay, of the AM wave and the carrier signal at the receiver, if it is having 90 degrees, then you are losing entire information. See, if there is no phase difference, then you are getting the message signal here. See, here AC square by 2 is nothing but some scaling factor. If you are if you are multiplying with the scaling factor of 2 by s square, then both will get cancelled. You will get m of t, message signal. But if there is a phase difference of 90 degrees, then you are losing complete information, right? Yes, very good, Rohit, very good. Okay, so this is called quadrature null effect. Quadrature null effect. Whenever there is the phase difference of 90 degrees, okay, then you are not getting any signal, or you can say you are getting 0, right? You are not getting any information. So this is called quadrature null effect. Suppose if phi lies between 0 and 90. If suppose phi lies between 0 and 90, then what will happen? Here the signal will get attenuated. Then the signal will be attenuated. Signal will be attenuated. Okay, so you can use synchronous detector in order to detect the modulating signal from the AM, okay, provided if there is no phase difference between the carrier signals of AM wave and the carrier signal at the detector which you are using. Okay, right. This is very, very important. So whatever the AM wave we have discussed, we can use AM wave for broadcasting. So in the AM radio, okay, from one point to multi-point, if you want to do the communication, you can use the AM wave. Okay, right. So what is the drawback in the AM? So you have observed regarding AM all the equations, and regarding the concept you have understood. Okay, now what is the drawback is there in AM? Is there any drawback? Yes, very good, Rohit, very good. See, if you observe this equation, you are having total transmitted power is nothing but the carrier power plus sideband power, right? See, the message is present in the sideband, but when you want to transmit the message signal, okay, so that time you have to give power to the carrier signal also, okay. And if you observe here, when you are considering the modulation index as 1, that time you are getting efficiency as 33%, right? So that means the most of the power you are giving to the carrier, right? So that is the drawback. So now we want to minimize the carrier power while you are transmitting the signal, because the message information is present in the sideband, right? Now let us try to eliminate the carrier power. Okay, so the next technique or the modulation is nothing but DSB-SC. See, if you observe the AM wave, if you observe, you are having two sidebands, upper sideband, lower sideband, and along with that you are having the carrier. If you are suppressing the carrier, then you are getting only the two sidebands. So that is nothing but double sideband and suppressed carrier. Double sideband, suppressed carrier. So here transmitted power is nothing but the carrier power plus sideband power. So here we are suppressing the carrier. So that means we are making this value 0. If you are making the carrier power as 0, then transmitted power is nothing but the entire power we have given to the two sidebands, right? So that means in this case you will get efficiency as 100%. Efficiency is nothing but sideband power divided by transmitted power. In this case, the moment if you are suppressing the carrier, transmitted power and sideband power both are same. So that means you are getting 100%. In the previous case, we are able to get only 33%. The moment if you are able to suppress the carrier, you are getting the modulation efficiency as 100%, right? So for the timing, okay, how how to get the DSB-SC signal? It is very simple. Whatever the modulating signal and whatever the carrier signal you are having, just you have to multiply. That's all. Just if you multiply these two, from there you will get only the two sidebands, but you won't get any carrier. You won't get any carrier. Okay. So for the time being, m of t you can assume as am into cos 2 pi fm into t, am cos 2 pi fm t. Similarly, carrier signal you can assume AC cos 2 pi fct. AC cos 2 pi fct. Okay, right. So here this one I am rearranging like this. AM into AC. Okay, multiply and divide with 2. Multiply and divide with 2. Then you will get 2 cos A cos B format. 2 cos A cos B. So once again same formula, cos sum plus cos difference. Cos sum plus cos difference. Okay, so this factor you can multiply with both. Okay, now if you observe here, in this entire equation, FC plus FM, this is nothing but upper sideband, and FC minus FM, this is nothing but lower sideband. So you are getting only two sidebands and there is no carrier component. So that's why it is double sideband suppressed carrier. Okay, right. So once again bandwidth you will get same. Bandwidth you will get 2 times FM. Bandwidth you will get 2 times FM. Okay. So regarding the power, PT equal to P sideband. Okay. So that is nothing but, once again same formula you can use. Whatever the peak value you are having, that peak value whole square divided by 2. Like that you are having two quantities. Okay, same peak value you are having, so you can multiply with 2. Multiply with 2. 2 will get cancelled. So from here you will get AM square AC square divided by 4. AM square AC square by 4. This is the total sideband power. This is the total sideband power. Okay, right. Now when you are transmitting the DSB-SC signal, okay, now how much power you have saved? Percentage of power saving. Percentage of power saving when you have used DSB-SC. Percentage of power saving when you have transmitted DSB-SC. See, here you have saved carrier power. Carrier power you have saved, right? So that will come in the numerator divided by the total power. Total power of AM signal, that is nothing but carrier power plus sideband power, right? So PC into 1 plus mu square by 2. Okay, if you want percentage, you can multiply with 100. PC will get cancelled. So if you rearrange, you will get 2 divided by 2 plus mu square into 100. 2 divided by 2 plus mu square into 100. So this one, if you want, you can rearrange like this. 1 minus mu square divided by 2 plus mu square into 100. So what is this factor? Can you guess? What is the second term? Mu square divided by 2 plus mu square. Previously we have discussed regarding AM. What is that? Yes, very good Rohit. This is the efficiency. This is the efficiency of AM wave. So that is nothing but 1 minus eta into eta of the AM wave. Mu square divided by 2 plus mu square is nothing but efficiency. Regarding modulation efficiency in AM wave we have seen. Modulation efficiency in AM wave, which is nothing but mu square divided by 2 plus mu square. Okay, right. So this is the percentage of power saving if you are using the DSB-SC. Okay, since we have saved the carrier power, so the carrier power will come into the numerator and out of the total power when you are transmitting with respect to AM. Okay, so after doing the simplification, you will get like this. Okay, you can remember either this formula 2 divided by 2 plus mu square, or you can remember 1 minus eta of the AM. Okay, whenever the question is regarding percentage, you can multiply with 100 like that. Now, here we have discussed regarding the standard equation of DSB-SC. Now, in order to generate this particular signal, we will use, can you guess what are the generators or modulators we are having regarding DSB-SC? Yes, very good, Rohit. Yes, we have balanced modulator and ring modulator. Balanced modulator and ring modulator. By using any of these two modulators, we can generate DSB-SC signal. And here if you observe, regarding the equation of DSB-SC, we are just multiplying two signals. We are just multiplying these two signals, right? So because of that, any particular modulator, any modulator which produces DSB-SC signal, we will call it as product modulator. We will call it as product modulator. Because the output of DSB-SC is nothing but simply the multiplication of two signals, right? Because of that, any modulator or any circuit which produces DSB-SC signal, we can call it as product modulator. Regarding demodulation of DSB-SC, so we are having synchronous detector. Once again, same phenomena, whatever we have discussed for AM, the same logic will applicable for here also, because we are using same synchronous detector only. Now, when compared to the amplitude modulated wave with the help of DSB-SC, okay, what we have reduced the amount of power that is required in order to transmit the signal. Okay, right? And still if you observe regarding the bandwidth, we are getting the same bandwidth. We are getting same 2 times FM. Okay. Now if you carefully observe, whatever the information you are having in the upper sideband, the same information is there in the lower sideband. Whatever the information is present in the upper sideband, the same information is present in the lower sideband, right? So instead of transmitting both the sidebands, if you are transmitting only this upper sideband or only the lower sideband, okay, that itself is sufficient, because ultimately you are getting the information. Ultimately you are getting the same information in both the sidebands. Suppose if you are transmitting either of the two sidebands, so because of that you can reduce the bandwidth of the signal and you can reduce the power also. Okay, so that means what is happening, with the help of DSB-SC we have suppressed the carrier. Now we are suppressing one of these two sidebands. Now can you guess what is the next modulator that we are discussing? We are suppressing one carrier and we are suppressing one of the two sidebands. Yes, very good, Raviteja. It is the single sideband suppressed carrier. Very good. Next one is SSB-SC, single sideband suppressed carrier. Single sideband suppressed carrier. Now regarding SSB-SC, the standard equation is, see, just observe here, you are getting AM AC by 2 into cos 2 pi FC plus FMT or cos 2 pi into FC minus FMT. So either you are getting plus or you are getting minus. Okay, either you are allowing this one or you are allowing that one, right? So for generalized case I am writing here AC AM by 2 into cos of 2 pi into FC plus or minus FM into T. Okay, if you are using plus sign, that means you are sending the upper sideband. If you are using minus sign, that means you are sending the lower sideband. Okay, one of the two sidebands we are transmitting, that's all. Okay, that's why here we are having only one sideband. So we are suppressing other sideband and we have suppressed the carrier. So because of that, the name of this modulation is single sideband suppressed carrier. Okay, so from here, if you want, you can expand later. So cos A plus B is nothing but cos A cos B minus sin A sin B. If you consider minus here, cos A minus B is nothing but cos A cos B plus sin A sin B. Accordingly, you will get. Okay, for the timing, I am not expanding. Now for this signal, if you write the power is nothing but you are having simply one cos signal. So once again the same formula, whatever the peak value you are having, perform square of that and divide with 2. So that means you will get AC square AM square divide by 4 and divide by 2 you are having. Together you can write divide by 8. Divide by 8 you can write. AC square AM square by 8. Now can you guess what is the percentage of power saving? Percentage of power saving if you are using SSB-SC. See, if you are using SSB-SC, you are using only one sideband. That means you have saved the carrier power and you have saved one of the two sidebands. See, if you are having both the sidebands, then the formula is PC mu square by 2. That is the total sideband power. So one of the sideband power you have saved. That means PC mu square by 4. Okay, right. And when you compared with the AM wave, so regarding PT is nothing but PC into 1 plus mu square by 2. See, it is very simple. This is the standard equation when you are having AM. If you want to transmit the power, if you want to transmit the signal, the amount of power required is carrier power plus total sideband power. So this is the carrier power we have saved. Okay, and this is the sideband power, total sideband power. That means two sideband power is PC mu square by 2. One of the sideband power means half of that one. That is nothing but PC mu square by 4. Right. So you can take PC as common, then PC will get cancelled. After that, you will get 1 plus mu square by 4 divided by 1 plus mu square by 2. If you want in terms of percentage, you can multiply with 100. Now, if you observe this particular signal, okay, so this particular signal will exist from either carrier frequency to FC plus FM, or you can say FC minus FM to FC. Okay, either of the two sideband. From there you are getting bandwidth as FM only. So that means if you observe with respect to AM signal, with respect to amplitude modulated signal and SSB-SC signal, what is your observation point? We have reduced the bandwidth of the signal and we have reduced the power required for transmitting the signal, right? So both the advantages we got if you are using SSB-SC signal. Okay, right. Now, how to generate the SSB-SC signals? Which modulators we will use? Generation of SSB-SC. We have two modulators. One is frequency discrimination method frequency discrimination method, and the other one is phase discrimination method. By using any of these two methods, we can generate SSB-SC signal, right? Now, coming to the demodulation, we will use synchronous detector. Just like the previous cases, we will use synchronous detector. Now tell me whether is there any quadrature null effect present here or not. See, in the DSB-SC, in the AM wave, we have discussed that quadrature null effect. Whenever there is a phase angle 90 degrees difference is there, then because of that you are getting output as 0. That is called quadrature null effect, right? So that is the case we have observed in the previous two cases, whether that particular phenomenon is happening here or not in the SSB-SC. Yes, very good Rohit, very good. Here there is no quadrature null effect. Okay, see, previously I have written the equation for single tone. Okay, when I have considered modulating signal as AM cos 2 pi FM into T. Okay, for generalized case, if you consider, if you assume M of T, okay, then the standard equation you will get regarding SSB-SC like this: AC by 2 into M of T cos 2 pi FCT, AC by 2 M of T cos 2 pi FCT minus plus AC by 2 M cap of T into sin 2 pi FCT. So here M cap of T is nothing but, with respect to M of T, there is a phase shift of 90 degrees, that's all. Okay, see, actually you can visualize from here. When you write cos A plus B is nothing but cos A cos B minus sin A sin B. Similarly, if you consider cos A minus B, accordingly you will get cos A cos B plus sin A sin B, right? So from there, for generalized case, you will get like this. Okay, this is the modulating signal. Here there is a phase shift of 90 degrees. This is the carrier signal. There is a phase shift of 90 degrees, right? So if you are using, this is the standard equation for generalized case, and if you are using synchronous detector, that means you are multiplying the signal with the carrier signal, that's all, right? So from there you will get output of low pass filter as AC square by 4 into M of T cos phi, AC square by 4 M of T cos phi minus plus AC square by 4 M cap of T sin phi. Okay, right. You will get the signal like this. If there is the phase shift between the carrier signal which you are using at the receiver and the carrier signal which is there in the modulated signal. Okay, right. So now if you consider, if phi equal to 0, then cos 0 is 1, so that means you are getting this signal. Sin 0 will be 0, so this entire quantity will become 0. So that means you are getting AC square by 4 into M of T. Okay. Similarly, if you consider phase angle is 90 degrees, then cos 90 is 0, that means the first term becoming 0, but sin 90 is 1, that means you are getting this term minus plus AC square by 4 M cap of T. So this is just 90 degrees phase shift of the modulating signal. That means either you are using, even if there is the 90 degrees phase angle difference between the carrier signal which you are using at the receiver and the carrier signal which is present at the modulated signal, even though there is the 90 degrees phase shift, but still you are getting the modulating signal. So that means there is no quadrature null effect. there is no quadrature null effect if you are using SSB-SC receiver. So in this way, you are getting three advantages. One is bandwidth reduced, and we have reduced the power required for transmitting the signal, and even if you are using synchronous detector, there is no quadrature null effect. Okay, right. But here in the SSB-SC signal, we are transmitting either only the upper sideband or we are transmitting only the lower sideband. That means from carrier frequency to FC plus FM or from FC minus FM to FC. That means ideally speaking, if you are having the filter, okay, if you want to pass either upper sideband or lower sideband, you will use one band pass filter. Okay, if you are using ideal band pass filter, that time what will happen? You are having sharp cutoff frequency, so you can allow only the respective band, either upper sideband or lower sideband. But practically the cutoff frequency will not be sharp, right? So it will pass some other set of frequencies also, right? So that means now can you guess this particular SSB-SC we can use for what kind of signals for transmitting? I am repeating my question once again. Since we don't have ideal band pass filters practically, that means we don't have sharp cutoff frequencies. Now if you want to use, since we are having multiple advantages, what are the advantages we already discussed with respect to SSB-SC, but there is a problem with respect to the set of frequency. So now which kind of signal we can use for transmitting with the help of SSB-SC? Can you guess? See, for voice signal, we already discussed. For voice signal, the range is what? 300 Hz to 3500 Hz. Okay, so in general, whenever you are drawing any spectrum in the frequency domain, okay, in general we will draw the spectrum for both positive frequency axis and similarly negative frequency axis, right? So that means, so here this particular signal is starting from 300 Hz. Similarly here on the left hand side you are having minus 300 Hz. That means here what is the range of frequencies you are having? 300 to minus 300. So you are having 600 Hz. See, practically speaking, there is no negative frequency, but whenever you are drawing the spectrum, we can draw whatever the positive frequency axis you are having accordingly the symmetrical negative side. Okay, so that means you are having 600 Hz band. Okay, so during this 600 Hz, you are not using any information, right? So that means if you are using SSB-SC for transmitting the voice signal, since you are having 600 Hz, there is a separation. Okay, so whenever you want to transmit one sideband, either upper sideband or lower sideband, okay, so you can transmit voice signal with the help of SSB-SC, because here you are getting 600 Hz. By default, you are getting some gap. Okay, and in this gap, there is no information at all. That means you are not losing any information, and since you don't have ideal band pass filters practically, okay, and so this is the best thing. Even if suppose there is no sharp cutoff frequency at 300 Hz, suppose if it is accepting 250 or 280 also, there is no problem because there is no information at all, right? Okay, so that means we will transmit voice signals with the help of SSB-SC modulation. I hope it is clear for everyone. Now the next one is VSB-SC modulation. Vestigial sideband suppressed carrier modulation. Here, this is nothing but whatever the single sideband only, but along with that, you will pass in the other sideband some range of frequencies, right? So this modulation we will use for, can you guess? This modulation we will use for transmitting what kind of signal? See, you can easily remember, here you are having V, right? So this one we will use for transmitting video signal. Video signal. Video signal frequency range is 0 to 4.5 megahertz. 0 to 4.5 megahertz. So for transmitting video signal, we will use DSB-SC. Even regarding voice signal other name is what? Speech signal. Speech signal, right? So here in the letter speech, in the word speech, the starting letter is S, right? So we are using SSB-SC. So in this way you can easily remember. For transmitting speech signal or voice signal, we are using SSB-SC. For transmitting video signal, we are using DSB-SC. So with this we have covered regarding first chapter. So in this particular chapter we have discussed regarding amplitude modulation, regarding DSB-SC, regarding SSB-SC and DSB-SC. Okay. So for all the modulation techniques we have discussed the standard equations, and regarding the bandwidth, regarding power calculations, modulation efficiency, percentage of power saving and applications where we are using the respective modulation technique. And regarding the generators or modulators we have discussed, regarding detectors or demodulators. Okay, so I hope it is clear for everyone. I hope all of you got the overview regarding first chapter. So now let us move on to the second chapter. So all of you put the heading chapter 2, angle modulation. So first write the carrier signal C of t equal to AC into cos of 2 pi FCT plus phi. So this one if you want you can write like this, AC into cos of theta of t. Okay, right. Yes, very good Ravitejo. So here whenever you are having cos signal or sin signal, okay, you are having the peak value or magnitude or amplitude and you are having the angle. Okay, but here we are writing this angle as like this, 2 pi FCT plus phi. Okay, so here you are having the frequency component, here you are having the phase component. So that means if you are varying the frequency or if you are varying the phase angle, so that means accordingly the angle of this particular carrier signal is varying. Yeah, very good evening Atul. Okay, so the moment if you are varying the carrier frequency or if you are varying the phase angle, okay, so that means the angle of this particular carrier signal is varying, right? So that means if you are varying any of these two quantities in accordance with the modulating signal amplitude, then we are calling this particular modulation method as angle modulation. So previously we have discussed in the first chapter regarding the variation of the peak, variation of the amplitude of the carrier signal in accordance with the modulating signal. Now we are discussing regarding frequency and regarding phase angle. Okay, so that is together as called as angle modulation. So accordingly you are having two modulation techniques here. One is frequency modulation, FM, and the other one is PM, phase modulation. Frequency modulation, if you are varying the frequency, then accordingly we are calling it as frequency modulation. If you are varying the phase angle, then it is called phase modulation. So here we are having theta of t is equal to For generalized case, I am writing 2 pi f I t plus phi. See, this is the carrier frequency you are having when there is no modulation. But suppose if you are varying the carrier frequency, okay, then the corresponding frequency I am labeling as f suffix I, that is nothing but instantaneous frequency. Okay, so for generalized case I have considered like this: theta of t equal to 2 pi into phi of t plus phi. So just do the derivative on both sides. D theta of t divided by dt, which is nothing but 2 pi f phi is the constant you can keep outside. So derivative of t, you will get 1. Derivative of phase angle, you will get 0. So from here you can write this equation as f phi is equal to 1 by 2 pi into d theta by dt. D theta by dt. Similarly, all of you just give a try how we can write theta of t in terms of phi, in terms of f phi. All of you give a try. Yes, very good, Raviteja. Yes. So we can rearrange this one as theta of t equal to 2 pi into integral f phi dt. Theta of t equal to 2 pi into integral f phi dt. Right. Okay. So for the timing, let us consider frequency modulation. Later we'll discuss regarding phase modulation. Okay. So here regarding instantaneous frequency, fi equal to fc plus kf into m of t. Fi equal to fc plus kf into m of t. See, when there is no modulation, then that time you are getting only the carrier frequency, that is the initial. Okay. But now in accordance with the kf, okay, according the variation is happening in addition to the frequency of the carrier, whether it may increase or it may decrease. Okay, let us see regarding that. So here you can assume m of t as am cos 2 pi fmt. So that means fc plus kf into am cos 2 pi fm into t. Okay. So here cos value, maximum value will be plus 1 and minimum value will be minus 1, right? So that means accordingly you will get fc plus, either you will get fc plus kf into am, or you may get fc minus kf into am. Okay, so that means this kf into am you can write it as delta f, so which is nothing but frequency deviation, Okay, so that means the reference signal frequency, carrier frequency you are having fc, okay, that may go maximum value as fc plus del f or minimum value as fc minus del f. That means the carrier frequency here, if you are using frequency modulation, okay, in accordance with the amplitude of the modulating signal, it will vary between two frequencies. The minimum value is fc minus del f and maximum value is fc plus del f. That means here the frequency of the carrier signal is varying in accordance with the modulating signal amplitude. That's why we are calling this one as frequency modulation. Frequency modulation. Now, you can write the standard equation for FM signal like this. S of t equal to, for generalized case you will get like this, AC into cos 2 pi FCT plus 2 pi kf integral m of t dt. 2 pi kf integral m of t dt. See, if you are generalized case, if you are considering the single tone modulating signal is nothing but m of t, right? So here theta is nothing but 2 pi into integral fi dt, where fi is nothing but this entire function. Fi is nothing but this entire function. So just substitute here. So from there you will get this equation. S of t equal to AC into cos theta of t, where theta of t is nothing but 2 pi into integral fi dt, where fi is nothing but this entire function, right? So 2 pi into fct plus 2 pi kf integral m of t dt. Okay. So if you are considering m of t as am cos 2 pi fmt and then perform integration of cos signal and just do the simplification, from there you will get the equation like this. If m of t equal to am into cos 2 pi fmt, then you will get s of t as, directly I am writing, s of t you will get AC into cos of 2 pi fct plus beta sin 2 pi fmt, where beta is nothing but modulation index, where beta is equal to delta f by fm. So beta is nothing but modulation index. See, it is very simple integration. Integral cos is nothing but sine you will get, and regarding 2 pi fm you will get in the denominator 2 pi will get cancelled. So in the numerator you are getting kf am and denominator you are getting fm, right? So you can write here kf am by fm. Or previously we got regarding delta f is nothing but kf am. Okay, so from there also you can write like this. Okay, I am repeating once again, it is very simple. So integral cos is nothing but sine function you will get, and regarding 2 pi fmt you will get 2 pi fm in the denominator. Okay, so 2 pi will get cancelled. So in the numerator you are having kf am and denominator you are getting fm. So kf am is nothing but delta f. Okay, so you are getting delta f by fm, so which is nothing but modulation index. Okay, so if modulation index is less than 1, then we will say it is the narrow band FM, and if the modulation index is greater than 1, then we will say it is the wideband FM. So that means we are having two types of frequency modulation based on the modulation index. Okay, if modulation index is less than 1, we are calling it as narrow band. If modulation index is greater than 1, then we are calling it as wideband. Hi Mayank, good evening. Okay, so just consider this signal, and here for the timing let us consider narrow band. So that means beta value is less than 1. Okay, so here you are having cos of a plus b. Cos a plus b is nothing but cos a cos b minus sin a sin b. Okay, so regarding See, the moment if beta value is less than 1, this overall value will become less than 1, right? So then cos of very small value is nothing but almost you can assume like cos 0. Cos 0 is nothing but 1, right? Similarly, whenever you are having the entire phase angle value, if it is smaller, then sine of theta is almost equal to theta, right? So if you do like that approximations, from there you will get the equation like this. For narrowband FM, narrowband FM means beta value is less than 1. So you will get S of t as AC into cos 2 pi FCT. S of t equal to AC cos 2 pi FCT minus beta AC into sin 2 pi FCT into sin 2 pi FMT. See, I am repeating once again, cos A plus B is nothing but cos A cos B, right? So just observe here, I have written cos A. Regarding cos B, I haven't written because here beta value is less than 1. So the moment beta value is less than 1, cos of this overall value you will get almost closer to 1. Just like cos value, cos 0 is nothing but 1. So in that way you can approximate. Okay, minus sin A sin B, sin A sin B. Okay, so regarding sin B, so whenever you are having smaller phase angle, okay, sin theta is nothing but theta. So that means this entire quantity you will get. Okay, you have to multiply with AC. So that means you are getting beta AC into sin 2 pi FMT. I hope it is clear for everyone. Now the first parameter you can write as it is AC into cos 2 pi FCT minus, here just multiply and divide with 2. Multiply and divide with 2. Then you are having 2 sin A sin B. 2 sin A sin B is nothing but cos difference minus cos sum. Cos difference minus cos sum. Cos difference minus cos sum. Right? Okay. So multiply this quantity with both. You will get first parameter I am writing as it is AC cos 2 pi FCT. Then first I will consider this one because here minus into minus you will get plus beta AC by 2 cos of 2 pi into FC plus FM into T. Next, here you are getting minus beta AC by 2 cos of 2 pi into FC minus FM into T. Now just observe this equation. How many frequency components you are having? Just observe this equation. How many frequency components you are having? Yes, very good Raviteja, very good. We are having 3 frequency components. See, this is the first one, FC, carrier frequency. This is the upper sideband, and this is the lower sideband. We are having 3 frequency components, right? FC, FC plus FM, FC minus FM. Yes, very good, Mayank. Okay. Now, if you observe with respect to your standard AM equation, so there also you are getting like this component, okay, and there also you are getting like this component, and there also you are getting like this component, but there you are getting plus sign, right? So that means you are having carrier frequency, upper sideband, lower sideband. Okay. Now, if you observe, when compared to the standard AM equation and the narrowband FM, there is the similarity is there. When you consider only the magnitude wise, the magnitude spectrum of narrowband FM and AM both are same, right? But if you observe regarding the carrier frequency and upper sideband, with respect to these two, the lower sideband, the component, you are getting 180 degrees out of phase. Okay, right. So that is the difference. Otherwise, there is a similarity between AM and narrowband FM. Okay, even if you calculate the power, you will get the power similar to that of your AM, PC into 1 plus beta square by 2. See, previously for AM, you are getting PC into 1 plus mu square by 2. Similarly, here modulation index is beta. You follow the same approach. Whatever the RMS values here you are having, whatever the peak values you are having, just perform square of that, divide with 2, and just add all of the powers and do the simplification, you will get this one. So if you compare this equation with the transmitted power regarding AM wave, okay, both are similar, where here beta is the modulation index of narrowband FM, there mu is the modulation index of AM, right? So that means regarding the transmitted power there is a similarity, regarding the number of frequency components there is a similarity. Even if you compare the bandwidth you will get same 2 FM only, same 2 FM. So that means since there are the similarities between the AM wave and narrowband FM, okay, so we will never use narrowband FM because we already discussed regarding the drawbacks of AM. What are the drawbacks of AM? You are transmitting more power. If you actually the information is there one of the sideband, but you are supposed to transmit even the carrier power. Because of that, you are getting modulation efficiency as 33% only. That means most of the power it is going in the carrier, right? So that is one of the drawback. And regarding bandwidth also you require more. Okay. So since we have discussed regarding the drawbacks of AM, and since narrowband FM is similar to AM, so we will never use narrowband FM. I hope it is clear for everyone. Why we never use narrowband FM? Regarding FM, why we are not using narrowband FM? I hope it is clear for everyone. Okay, so obviously we will use wideband FM. So that means beta value is greater than 1. Okay, right. So regarding wideband FM, so here you will use the Bessel function. This is the Bessel function. Jn of x is equal to 1 by 2 pi integral minus pi to pi e power j of x into sin theta minus n theta into d theta. So regarding Bessel function properties, j minus n of x is equal to minus 1 whole power n into jn of x. So that means for even powers, if n value is even number, then you will get regarding negative n value here and regarding positive n value, both regarding magnitude wise, both you will get same, because whenever you are having even number, square of minus 1 whole power even number, you will get positive value. But whenever n value is odd, for all the odd values of n, so the negative Bessel coefficient you will get minus of the positive Bessel coefficient. Okay, right. And one more property regarding Bessel function, summation over n equal to minus infinity to infinity, jn square of x is nothing but 1. If you are performing square of all the Bessel coefficients, okay, then you will get the equivalent value, you will get 1. So regarding standard equation or time domain equation of wideband FM time domain equation, S of t equal to AC into summation over n equal to minus infinity to infinity, Jn of beta into cos of 2 pi into Fc plus Nfm into t. S of t equal to AC into summation over n equal to minus infinity to infinity, Jn of beta, you are getting the Bessel coefficient here, and cos of 2 pi Fc plus Nfm into t. Okay, if you are considering n value negative, you will get Fc minus accordingly the multiples of Fm. Okay, similarly if you are considering positive n values, you will get Fc plus integer multiples of Fm, like that. Okay, so if you observe this particular equation, you are having, since n value starting from minus infinity to infinity, so here if you are considering n value 0, then only you are getting the carrier frequency cos 2 pi Fct. But if you are starting from minus infinity and if you are going up to infinity regarding n value, you are getting the number of frequencies you are getting starting from somewhere towards minus infinity towards up to plus infinity, right? So that means theoretically speaking or ideally speaking, regarding this particular signal, the bandwidth is infinite. Theoretically you are getting bandwidth as infinite. Okay, but practically beta plus 1 upper sideband frequency components, similarly beta plus 1 lower sideband frequency components, together you are having 2 times beta plus 1. So beta plus 1 upper sideband and beta plus 1 lower sideband. So if you consider this spectrum, okay, so when you consider the magnitude of this one, this is giving 99% when compared to the total. Okay, so that means regarding bandwidth, we will consider only these spectral components. So accordingly, you are getting the bandwidth as 2 into beta plus 1 into Fm. 2 into beta plus 1 into Fm. So this one you are getting according to Carson's rule. Theoretically speaking, for wideband FM, theoretically the bandwidth is infinite. But whenever you want to transmit any signal, the bandwidth should be as minimum as possible, so that you can transmit more number of signals, right? That's why even if you observe regarding first chapter, when we have discussed, our main intention, we have focused on two quantities. One is regarding the power required for transmitting the signal, and one more quantity we have focused regarding the bandwidth of the signal, right? Okay, similarly here, even though theoretically you might be having infinite frequency components, because of that you are getting infinite bandwidth, but when you calculate, when you represent all the quantities in terms of by using Bessel coefficient, then 99% of the magnitude you are getting if you are considering beta plus 1 upper sideband frequency components, beta plus 1 lower sideband, together you are having 2 times beta plus 1. So just multiply that one with FM. That's all. That is your bandwidth of wideband FM. Bandwidth of wideband FM. So what is your observation regarding bandwidth when you look at this formula? What is your observation when compared to the AM? When compared to the amplitude modulated wave regarding bandwidth? Which one is having more bandwidth? Whether AM is having or this one is having? See, obviously wideband FM is having more bandwidth when compared to AM, correct? See, bandwidth of AM is just 2 FM, okay? So there you're having FC plus FM, FC minus FM. Among all, FC plus FM is the larger, FC minus FM is the smaller. If you take the difference of those two, okay, then you will get 2 times FM, okay? But here you're getting 2 times beta plus 1 into FM. So that means when compared to the AM, the bandwidth of FM is more, okay? The bandwidth of FM is more. And one more observation point. Regarding AM, the bandwidth is independent of modulation index, but here it depends on the modulation index. Okay. Next, if you observe this particular equation and if you write the formula regarding power, you will get power required for transmitting the signal. You will get AC square by 2, so which is nothing but PC. See, actually you are having cos signals, right? So whatever the peak value you are having, you have to perform square and divide with 2. So like that you are having starting from minus infinity to infinity. So according to this formula, when you apply this one, you will get 1, right? When you have taken common, Jn square of beta is nothing but 1, okay? So simply you are getting AC square by 2, so that is nothing but carrier power. Now if you observe this one, in order to transmit the FM signal, how much power is required, and similarly in order to transmit AM signal, how much power is required? When you compare these two equations, okay, in which case you require more power in order to transmit the signal? Yeah, thank you, Vipin. Yes, very good, Mayank. Yeah, in the AM case, you require the power as carrier power along with the total sideband power. But here you require only the carrier power, right? So when compared to the AM signal, in order to transmit the wideband FM signal, it requires less power. But coming to the bandwidth, it may require more, okay, when compared to the AM signal. Now, if you observe here, when you draw this particular signal on the spectrum, on the frequency spectrum, okay, you will get n number of frequencies starting from minus infinity to infinity, okay? So, but here if you observe regarding this particular function, okay, Jn of beta, okay, regarding Bessel function Jn of beta decreases as n increases. As n value increases, Jn of beta value will decreases. So that means whatever when you have considered n value as 0, that means you are getting the frequency component related to carrier, right? But other than that, if you are considering any other frequency, that means as you are increasing n value, you are getting other frequency components are nothing but simply sideband frequency components, right? So as n increases, Jn of beta value decreases. That means now can you guess among all the frequency components, which frequency component is having highest value you are having? Can you guess? See, just observe this particular statement regarding Bessel coefficient. As n increases, Jn of beta decreases. Now can you guess, when you are having infinite frequency components, among all the frequency components, which frequency component is having highest value regarding Jn of beta? Obviously, you can start with n value 0. When you substitute n value 0, you are getting cos 2 pi fc, right? So regarding carrier frequency only, you are getting Jn of beta as maximum, okay? But for remaining all the frequency components, all the other sideband frequency components, your magnitude of the spectrum you are getting decreasing because of the Bessel coefficient, right? So that means here regarding J0 of beta is nothing but the Bessel coefficient correspond to the carrier frequency, right? So J0 of beta will be 0 will be 0 for few cases. Is 0 for when you're having beta values 2.4, 2.4, 5.5, 8.6, 11.8, like this. Like this you are having, okay, for these beta values, J naught of beta is becoming 0. Okay, see, you just remember for one case, you remember 2.4, just add 3.1, you will get this number, just add 3.1, you will get this number. After this, you have to add 3.2, then you will get 11.8. For initial two cases, 3.1, for this case, you can add 3.2, okay, that's all. Now, the moment if carrier frequency component becoming 0, that means remaining simply you are having sidebands. Right? So that is the advantage. So if you want to use wideband FM, so you have to suppress the carrier. You can suppress the carrier if you are choosing any of these beta values. Then because of that, the Bessel coefficient becoming 0, the moment if Bessel coefficient is 0, the corresponding frequency component peak value becoming 0. That means entire spectrum you are having simply sidebands. There is no carrier frequency, right? So that means that is the advantage. If you want to use wideband FM, if you want to save the power, okay, you can save the power that is required for transmitting the wideband FM signal, provided if you are choosing the beta values any of these. Okay, I hope it is clear for everyone why we are using wideband FM when compared to the any other modulation technique. Okay, with respect to AM we have discussed. Okay, with respect to AM, DSB-SC is better when compared to DSB-SC. SSB-SC is better. Okay, similarly VSB-SC we can use for video signal, like that. Okay, based on the application we can use accordingly the respective modulation technique. AM and FM we can use for broadcasting. Okay, and one more advantage here, whenever you are using frequency modulation, that means whatever the information is there in the modulating signal, that one is varying in the frequency of the carrier signal. Okay, so whenever the information is present in the carrier frequency, with the help of carrier frequency we are transmitting the information. So because of that the noise effect is less, right? So that is the advantage of FM when compared to the AM. Okay, so coming to the bandwidth, here we are having 2 into beta plus 1 into FM. So if you substitute beta values delta F by FM, so all of you try once, what you are going to get, 2 into delta F by FM plus 1 into FM. Then just do the simplification, you will get 2 into delta F plus FM. So you can use this formula or you can use this formula based on the given data. Okay. Now, generation of wideband FM. Generation of wideband FM, we are having two methods. First one is direct method and second one is indirect method. Direct method means here we will use VCO, voltage controlled oscillator we will use. So here input you are getting in terms of voltage, but output you will get in terms of frequency. So that means the carrier frequency is varying accordingly with the modulating signal amplitude, right? So directly with the help of VCO, you will get directly the corresponding FM signal. Okay, in the indirect method, first we will get narrowband signal, narrowband FM. After that, we will use some nonlinear device. With the help of that, we can get the wideband FM. Okay, so say for example, if you are using some nonlinear device, okay, Suppose if it is performing square of the input, then suppose I am giving here cos theta, then output you will get cos square theta. That one by using trigonometric equations, that one you can convert into 1 plus cos 2a divided by 2. So that means regarding frequency you are getting 2 times. Okay. See, first you will write cos square theta. Cos square you can write as 1 plus cos 2a by 2. Okay. So for the timing, my intention is, if you are having frequency component value something here, then if you are performing squaring, then you will get here multiplication. Okay. Similarly, with this understanding, suppose if I am transmitting cos theta, cos or sine signal, no problem. Now can you guess what is the here you are getting regarding cos? Can you guess? Here you are having square, so because of that you are getting 2. Similarly, here you are having n, right? So that means you will get n theta. Simple. You will get n theta, right? So that means say for example, if you are having AC into cos, the FM equation like this, AC into cos of 2 pi FCT plus beta into sine 2 pi FMT. So this is the FM signal we are having. If you are passing this one through a non-linear device which is having power n, then because of that what will happen here? You will get AC, you will get as it is, okay, cos of. Now this entire angle multiplied by n, so because of that I am directly writing here 2 pi into NFC into T plus n into beta into sine 2 pi FMT. See, just for easy understanding, assume this entire quantity as theta, just like here. Entire quantity you can assume theta. Now if I have passed this one through a non-linear device which is having power n, so because of that here angle becoming n times. Okay. So when you multiply this entire angle with n, FC become NFC and here beta become n beta. So now what is your observation? Whenever you are passing any FM signal, through a non-linear device which is having power as n, then at the output there is a change in the frequency of the carrier signal. FC becomes n times FC and beta becomes n times beta. Now can you tell me, is there any change in the FM? Is there any change in the FM at the output? There is no change. Yes, very good, Mayank. There is no change in the frequency of the modulating signal. Only there is a change in the frequency of the carrier signal and there is a change in the modulation index. But there is no change in the frequency of the message signal. Okay, right. Next one regarding demodulation of wideband FM. So here we are having two methods. One is frequency discrimination method. Frequency discrimination method. Another one is phase discrimination method. Do you know the example for this one? Yes, Mayank. Whatever the concepts we are having, okay. So for each and every concept, you should know the operation, and regarding each and every concept, whatever the mathematical equations or formulas you're having, you can remember, okay. That you can remember with the help of practice, okay. Now you will get the questions sometime directly based on the formulas you will get, and sometimes regarding the operation of the circuit, based on that also you will get. Okay, here for easy understanding, we are considering am into cos 2 pi fm into t, that is the message signal, right? So instead of that, they can give any other signal also. So then if you are having the operation of the circuit, then you can solve that question. Or even if you are having the standard equations regarding am, what is the standard equation, regarding DSB-SC, what is the standard equation. So accordingly, if you substitute and do the derivation from there also, you can solve like that. Okay, for each and every concept, you should know the operation of the circuit, and you should know the whatever the formulas are there, okay, standard formulas. So these formulas are very important. Yes, regarding frequency discrimination, we are having balanced slope detector, and regarding phase discrimination, we are having PLL, phase locked loop. Phase locked loop. See, in this phase locked loop also, you are using one low pass filter, and with the help of VCO, you will generate the local oscillator carrier. Okay, instead of generating local oscillator carrier, so with the help of VCO, you can generate the carrier frequency. So it is forming a loop. Okay, so there we are using the phase locked concept. So from there you can get the message signal or modulating signal. Okay, right. So this is about FM, and regarding PM, regarding phase modulation, S of t, the time domain equation is AC into cos of 2 pi fct plus Kp into m of t. Kp into m of t. So here Kp is the phase sensitivity, AC into cos of 2 pi fct plus Kp into m of t, you can assume as am cos 2 pi fmt, cos 2 pi fmt. So here Kp into am is nothing but the phase deviation, delta phi cos 2 pi fmt. Okay, right. Cos 2 pi fct plus delta phi into cos 2 pi fmt. So here delta phi is nothing but Kp into am. So here this one we will call it as beta, modulation index. For phase modulation also, the modulation index is nothing but delta phi, or phase deviation, which is nothing but Kp into am. Kp into am. So regarding this particular signal, the transmitted power is nothing but peak value AC square divided by 2. And regarding bandwidth, same formula, whatever you have used in FM, same formula will applicable, but only the difference regarding modulation index, the formula will vary, that's all. Here modulation index is nothing but Kp into am or del phi. Okay, right. So just write regarding the FM equation and PM equation once. Regarding FM and regarding PM, just write the equations once. S of t equal to AC into cos of 2 pi fct. For generalized case, I am writing 2 pi kf integral m of t dt. 2 pi kf integral m of t dt. Similarly for PM, S of t equal to, just now we have discussed, AC into cos of 2 pi fct plus Kp into m of t. Kp into m of t. For generalized case, I have considered. M of t is the modulating signal for generalized case. For Fm, you are getting cos of 2 pi fct plus 2 pi kf integral m of t. Integral m of t you are having, whereas for Pm, you are having Kp multiplied by m of t. That's all. Okay. Now, if you are having phase modulator, you can convert. Okay, you can generate Fm equation, or if you are having Fm modulator, you can generate Pm equation. Okay, so it is very simple. Suppose you are having Fm. So by using Fm, you are getting this equation. But now, suppose by using Fm, if you want to generate PM, just observe here. You are having m of t here, but here you are having integral m of t. So that means what we have to do? Here we will use. We will give m of t as the input. And we will use one differentiator. If you use one differentiator, then you will get dm of t by dt. Now that one we are giving in place of m of t. If you substitute dm of t by dt, derivative and integrative will get cancelled, right? So that means after that what you are getting? You are getting AC cos, both are same. 2 pi fct, same. Okay, here integration derivative both are get cancelled. After that you are getting m of t, but here you are getting 2 pi kf, but here you are having kp. That's all. That means if you are having Fm, if you want to generate Pm, okay, what you have to do? Just in front of Fm, you have to consider one more block, that is nothing but differentiator. If you are considering differentiator of differentiation of message signal, if you are passing through Fm, then here your output is nothing but Pm. Output is nothing but phase modulated signal. Similarly, if you are having PM, if you are having phase modulator, now if I want to get frequency modulated waveform, can you guess what is the block that I have to use here? See, it is very simple. Here you are having phase modulated signal. Here you are getting normal m of t. But if you want to get FM signal, you want to get integral m of t. So that means here I will use integrator. Okay, I will pass m of t signal through an integrator, then I will get integral m of t dt. Now, in place of m of t, now I will get integral m of t dt. Now you are getting FM signal. Yes, very good, Mayank, very good. Okay, you will get FM. But only the difference, it is very simple. By observing these two equations, 2 pi kf is nothing but kp. So if you rearrange this one, you will get kf equal to kp by 2 pi. That's all. Okay. So in this way, if you are having FM circuit, you can generate PM, or if you are having PM circuit, you can generate FM. That's all. Okay. I hope just if you remember these two equations for generalized case, you can solve any question regarding this particular concept, regarding FM or regarding PM. Okay. And we have discussed regarding modulation index, regarding power, all the formulas which are required, we already discussed. Okay, so with this we have completed regarding second chapter. So in the second chapter regarding angle modulation, we are having frequency modulation and another one is phase modulation. Okay, so regarding FM, we are having two types of modulation. One is narrowband FM, another one is wideband FM. Since there is a similarity between narrowband FM and AM, we are not using narrowband FM. So that's why we will use obviously wideband FM. So when compared to AM, okay, and wideband FM takes less power in order to transmit the signal. And when compared to the bandwidth of AM, obviously wideband FM is taking more bandwidth. Okay, but when compared to the noise, okay, whenever you are transmitting any signal in the amplitude, okay, in the analog, okay, in the amplitude modulation, there are chances because of the noise you may get errors. But if you are transmitting the signal with the help of frequency, okay, if you are transmitting the information with the help of frequency, there are less chances, right? So that's why obviously among all the modulation schemes, wideband FM is recommended. Okay, so in general AM and FM we will use for broadcasting. Okay, and regarding other modulation techniques we already discussed. Okay, and since there is a similarity, okay, if you want, because FM and PM, if you are having one circuit, we can convert into other circuit, vice versa, right? Okay, so with this we have completed so far regarding analog communication. Okay, so now in the analog communication, we have seen at the transmitter section modulator, at the receiver section demodulator. Okay, now let us see regarding receivers. Okay, regarding AM and FM receivers. Third chapter, chapter 3, AM and FM receivers. So whenever you are considering a receiver, yes, Mayank, I will discuss that one after some time. Okay, I am in the flow. Okay, so the third chapter is AM and FM receivers. So whenever you are having the receiver, okay, there are three characteristic parameters regarding any receiver. First one is sensitivity. Second one is selectivity. And third one is fidelity. So whatever the signal you are receiving at the receiver, okay, suppose, see, because you are transmitting the signal from very long place, so obviously whatever the signal you are receiving at the receiver, obviously it is having less strength, right? So it will be in the order of millivolt or microvolt, like that. Okay, so with the help of power amplifier, you can amplify the respective power of the signal. Okay, so there, if you are having, suppose whatever the signal you are receiving at the receiver, right, even if you are getting minimum signal strength, okay, but if you are using in that receiver, if the power gain of the amplifier is so high, so that if you are able to get regarding your optimum level whatever required at the output, okay, if you are able to get, then so that is nothing but sensitivity. Sensitivity is very simple. What is the minimum signal strength that you can receive at the receiver, so that with the help of your power gain amplifier at the receiver, you can get your desired output or optimum output at the receiver. Okay, so regarding selectivity, so whenever you are getting any signal, okay, that particular signal will be having some frequency, right? So you will be having information in one particular frequency, and you will be having other frequency components may not be your required signal frequency. Okay, so that means you have to select the required frequency components. So that means your receiver should be better, or it should be like in such a way that it should select your desired frequencies and it should not select your undesired frequencies, or you can say that it should accept only the desired frequency range of frequency, and it should block the other frequencies which are not required. Okay, so it should be very selective in terms of the frequencies. Okay, right. And then fidelity. So here receiver, it should produce whatever the valid output is there for all the frequencies. Whatever the frequencies you are having the information, for all those frequencies it has to produce. Okay, so these are the three important characteristics whenever you are designing any receiver, either whether it is AM or FM. Okay. So regarding AM and FM, we are having similar receivers. So the first one is tuned radio frequency receiver. Tuned radio frequency receiver. So in short, you can call it as TRF, tuned radio frequency receiver. So here at the receiver, you will tune to a particular station. Okay. So here basically whatever the signal you are receiving, okay, you will be having n number of signals. Okay. So each particular signal is allocated for a particular bandwidth. Okay. So that means the moment if you are changing the resonant frequency, okay, so that means for each band you will be having, for each band of frequencies, you will be having one resonant frequency. So here in the tuned radio frequency receiver, here tuning means we are tuning to the corresponding resonant frequency. So whenever you are using tuned radio frequency, so that means can you guess what kind of filter you are using among low pass, high pass, band reject? Can you guess whenever the term resonant is there? I hope all of you studied in your network theory subject also. Resonance occurs in which filter? Yeah, resonance will occur in band pass filter, but the bandwidth will become very narrow, correct? Yes, it is a band pass filter. So we can say that any tuned circuit will act as band pass filter. Okay, but in order to happen resonance, so that bandwidth we are considering very narrow, like that's all. Okay, very narrow, so that you are focusing for a particular limited band, you are mainly focusing about one resonant frequency, correct? Right. So if you are using AM receiver, then here the range is 550 kilohertz, 550 kilohertz to 1650 kilohertz. So this is the frequency range it is allocated for AM signal. Okay, similarly for FM signal, the range is 88 megahertz to 108 megahertz. 108 megahertz. Okay, so here you are having this entire is like you can say bandwidth of the channel. Okay, but in this particular channel, okay, you will allocate each and every corresponding, okay, you will be allocated 10 kilohertz bandwidth. Okay, so here it is mandatory to maintain a bandwidth of 10 kilohertz. For each station is allocated for 10 kilohertz bandwidth. So that means if you are transmitting AM signal, now can you guess what is the maximum frequency signal that you have transmitted from the transmitter side? If you are using AM, okay, so for each AM station it is allocated, the bandwidth is 10 kilohertz. So if you know the bandwidth of the signal, from there you can guess what is the maximum signal frequency. For AM, what is the bandwidth? 2 times FM. So here 2 times FM is 10 kilohertz, so that means FM is 5 kilohertz only, right? Yes. And whenever you are using resonant frequency, that means tuned radio frequency or band pass filter, so I hope all of you know this formula regarding quality factor. Quality factor Q equal to FR by bandwidth. This one if you rearrange, you will get bandwidth as FR by Q. FR by Q. FR by Q. Yes, very good, very good. So here, if you are using tuned radio frequency, okay, for each station in the AM, it is allocated 10 kilohertz bandwidth. Okay, so that means in this 10 kilohertz bandwidth, you have to tune to the respective resonant frequency. Similarly, another 10 kilohertz bandwidth. In that, the middle frequency will be the resonant frequency of some other station. Like that, you are having for each station 10 kilohertz bandwidth is allocated. Now here, one of the most important thing is this one. If you are using 10 tuned radio frequency, since for each station it is allocated 10 kilohertz bandwidth, that means you have to smartly choose the resonant frequency. Okay, so here the important thing, in order to maintain 10 kilohertz, so here bandwidth is constant. Here right hand side, if you observe, you are having two parameters. One is resonant frequency, another one is quality factor, right? So the moment if you are changing resonant frequency, accordingly this quality factor also should change accordingly, so that the overall value should come constant. So that means practically the moment if you are changing resonant frequency, that means you are changing the frequency of the corresponding station of AM transmitter, right? So the moment if you are changing this frequency, accordingly the quality factor also should change. If it change, then if you are able to get constant 10 kilohertz bandwidth, then according to that particular station, you will get the information correctly. Suppose because of this quality factor some variation is there. Okay, suppose if you are getting bandwidth as, suppose you have chosen some resonant frequency, so for that resonant frequency, accordingly some quality factor it came. Okay, after doing some calculation here, you are getting bandwidth as greater than 10 kilohertz. Then what is happening? Some other station components information also you are receiving, right, which are not required for you. And suppose if you are getting bandwidth is less than 10 kilohertz, then what is happening? Whatever you have selected a channel, in that channel whatever the information you are supposed to receive, you are losing something, right? So that's why that is the drawback is there in the tuned radio frequency receiver. Okay, practically to maintain constant 10 kilohertz bandwidth for all the cases, the moment if you are adjusting resonant frequency, according to the quality factor also should adjust. Okay, so that's why what we used to do, in order to overcome this drawback, we will use super heterodyne receiver. Okay, so the next receiver is super heterodyne receiver. So here whatever the frequency you are receiving at the receiver, that one we can label as F suffix S. F suffix S. This is the carrier frequency of the tuned station. Carrier frequency of the tuned station. So this frequency we are down converting. Okay, so we will convert this one into intermediate frequency. Okay, so that is nothing but IF. IF is nothing but intermediate frequency. Okay, so here this frequency is fixed. Okay, so whatever the signal you are receiving, okay, with the help of some mixer circuit, we will generate either plus or minus some frequencies. Okay, if you are adding two frequencies, that is called up conversion. If you are subtracting, that is called down conversion. After that, in order to get this constant frequency, we will use the local oscillator frequency accordingly. Okay, so that means here you will get constant frequency. Whatever the drawback earlier was there with the help of tuned radio frequency, now we are able to overcome. Now in this case, we are not tuning to the AM transmitter resonant frequency. Rather, we are here in this case, we are tuning to this particular frequency. Okay, we are adjusting the local oscillator frequency in such a way that we want to get the constant intermediate frequency. So here, if you are using AM, then intermediate frequency is 455 kilohertz. 455 kilohertz. Whereas if you are using FM, the intermediate frequency is 10.7 megahertz. 10.7 megahertz. Okay, in super heterodyne receiver, tuning means changing the local oscillator frequency, right? And you remember these two formulas. Image frequency FSI is equal to Fs plus 2 times IF. FSI is nothing but image frequency, which is nothing but whatever the signal frequency you are receiving, that frequency you have to add with 2 times image frequency. Now this image frequency we have to suppress. So regarding that, you are having one parameter, image rejection ratio, IRR, image rejection ratio. From this parameter you will come to know how much image frequencies you are able to reduce with the help of your receiver. Alpha is nothing but square root of 1 plus q square rho square, where rho is nothing but q is the quality factor and rho is nothing but FSI divided by Fs minus Fs divided by Fs. See, it is very simple. FSI is nothing but the signal frequency plus 2 times intermediate frequency. So obviously when you observe these two, this is the larger. So you can perform the ratio of these two first and then take the ratio volta and subtract this one from here. That's all. Okay, so this is about AM and FM receivers regarding tuned radio frequency, regarding super heterodyne. So after this we will discuss regarding random process and noise, because we have discussed regarding analog communication, okay, regarding amplitude modulation, demodulation, similarly angle modulation, demodulation. Okay, we will discuss one simple concept here only. Actually this concept come under next chapter, but for the timing let us summarize here itself. Regarding figure of merit, figure of merit FOM is nothing but signal to noise ratio at the output divided by signal to noise ratio at the input. The ratio of output SNR and input SNR is nothing but figure of merit. Okay, so if you are using for DSB-SC, for SSB-SC, for VSB-SC, the figure of merit is same. Can you guess what is the value? For all these three modulations, figure of merit is same. Yes, very good, Mayank, very good. Figure of merit is 1. Output SNR, input SNR both are same. So when you take the ratio, you will get 1 for all these three cases. Okay. Whereas for AM, the figure of merit is equal to mu square divided by 2 plus mu square, which is nothing but the modulation efficiency. So in the AM, we have derived the modulation efficiency formula. Okay, mu square divided by 2 plus mu square. The same answer you will get even for figure of merit. Okay. Whereas for FM, the figure of merit is 3 by 2 beta square. 3 by 2 beta square. Okay, right. So with this we have completed regarding analog communication. Okay. So regarding random process and noise, after that digital communication, and then information theory. Regarding that we'll discuss after the break. So you can take 5 minutes break. Okay, we'll start the class at 7:30. Hello students, welcome back. So far we have discussed regarding first three chapters, that is regarding introduction to the communication system and amplitude modulation. After that we have discussed regarding angle modulation, and then we have discussed AM and FM receivers. Okay, now let us start the next chapter, that is random process and noise. Random process and noise. Okay, right? So I hope all of you studied regarding probability in your mathematics. Okay, so based on that one we are having, okay, two parameters regarding random process. Okay, so one is probability distribution function. So the first one is probability distribution function. Probability distribution function, or you can call this one as cumulative distribution function. Cumulative distribution function. So if you want in shortcut, you can represent as capital letters CDF, cumulative distribution function, or probability distribution function, PDF, capital letters, probability distribution function or CDF, cumulative distribution function. So in general we'll represent this one with the letter capital F, suffix capital X of small x. Fx of x is equal to probability of x less than or equal to x. Okay, so in the probability, in the mathematics you have studied for occurring an event or for not occurring an event, like that. Okay, but here we are considering the random variable. Okay, so we will represent integer values. Okay, we will consider some range. So up to that particular value, what is the distribution you are having? Okay, or after that particular value, what is the distribution we are having accordingly? Okay, right. So fx of x is nothing but probability of x less than or equal to x. So let us see the properties of PDF function. So obviously if you observe here, the probability distribution function is nothing but we are adding all the probabilities at each and every instant. Okay, so that means obviously if you observe, for occurring any particular event, whenever you are dealing about the probability, so regarding probability, what is the range in general you will be having regarding probability? If the event occurs, the probability is 1. If the event not occurs, 0. Or if you are having suppose some chances, accordingly then you will get in between 0 to 1, right? Right. So in the similar way, so this probability distribution function, the range also will remain same, because ultimately it is regarding probability only. Okay, right. So 0 less than or equal to fx of x less than or equal to 1. The probability distribution function value lies between 0 and 1. Lies between 0 and 1. And if you consider x value infinite, so that means it is reaching to the maximum value, that is nothing but 1. It is reaching to the maximum value 1. Similarly, if you are considering x value as minus infinity, that means leftmost side starting event you are considering, so that means the probability starting with 0, like that. Okay. Next, probability of x greater than x1. Probability of x greater than x1. If you want to calculate this one, see here you are having probability of x less than or equal to x, but here you are having probability of x greater than x1. So that means this one you can write like this: 1 minus probability of probability of x less than or equal to x1? Yes or no? See, the total probability is 1. From there, if you are subtracting this 1, that is nothing but the probability of x greater than x1, right? So, probability of x less than or equal to x1 is nothing but fx of x1. So, from here you can write 1 minus fx of x1. So, in this way, whenever in the question, if they ask to calculate this one, okay, if you know fx of x1, okay, so just subtract that value from 1. That is nothing but the probability of x greater than x1. Okay, so as the name implies, cumulative distribution function. Okay, as x value increases, okay, what is happening? You are adding probabilities. Okay, you are doing cumulative addition. So because of that, you can say that fx of x is an increasing function. It is an increasing function, right? So these are the properties of probability distribution function. So similarly, you will be having the other function as probability density function. Probability density function. So in short, we will represent this one as small letters, PDF. Probability density function. If PDF capital letters means probability distribution function, small letters means probability density function. So as the name implies, density means at any particular instant. Okay, so how much, what is the range, what is the frequency you are having, that is given the density, right? So that means here probability density function we will represent with the letter small letters fx of x, which is nothing but differentiation of probability distribution function, right? So fx of x equal to dfx of x divided by dx. So whenever you are performing like d by dt, that is nothing but rate. So similarly here we are dealing about random variables, so that's why we are doing differentiation with respect to x. Okay, if you are doing the differentiation of probability distribution function, you will get probability density function. Similarly you can write in other way, fx of x if you want to get, fx of x if you want to get, you have to perform integration. You have to perform integration of fx of x. So here the limits start from minus infinity up to x. Okay, so that you will get the distribution function in terms of x, like that. Okay, so here you are having regarding probability distribution function, this is the range, this is the range. Now here you are getting fx of x. Okay, now regarding the properties of PDF, integral minus infinity to infinity fx of x dx, fx of x dx, which is nothing but you will get 1. So whenever you are having, see here you are having probability density function, if you are performing integration from minus infinity to infinity, the overall value will get 1. Overall value will get 1. Suppose in the question, if they have given one waveform regarding probability density function of some random variable, okay, then if you perform the integration, if you are supposed to calculate the integration of that particular probability density function, that is same as integration is nothing but what? Integration is nothing but what? You might have studied in the networks also, you might have studied in the signals also. Integration is nothing but whenever you are having any curve or waveform, if you are supposed to calculate the integration of that particular waveform, integration is nothing but area, right? Area under the curve. Okay, so just simply you can perform area of that particular probability density function, and that one you can make equate to 1. So in the given probability density function, if any parameter is unknown, with the help of this property you can calculate that particular parameter, right? Yes, so whenever you are performing integration, that is nothing but area. Okay, next one, probability of x greater than x1. Probability of x greater than x1, if you want to calculate, okay, if you are having probability density function if you are having probability density function, you can perform the integration. The limits are starting from x1 to infinity, starting from x1 up to infinite, fx of x dx. Similarly, if you want to calculate probability of x less than x1, suppose if you want to calculate probability of x less than x1, now can you guess what are the limits? What are the limits I have to consider? See, for generalized case, this is the range, minus infinity to infinity. Okay, so since it is starting from x1, so I have considered the lower limit x1, upper limit as infinite. Okay, but here x less than x1, can you guess what are the limits I will consider here? See, the integration starting from where? Minus infinity. So you can start with minus infinity up to, this is the upper limit you are having, right? So that means here x1, that's all. If you know the lower limit, that one you can put here, upper limit is infinite. If you know the lower limit, if you know the upper limit, that means by default lower limit is this one, you can consider upper limit is this one, like that. Okay, right, very good Mayank, very good. So here the limits are minus infinity to x1, you will perform integration of fx of x dx. Similarly, with this understanding, if you want to perform probability of x1 less than x less than or equal to x2. Now can you guess what are the limits I have to consider? So whenever you are having probability density function, you will perform integration in order to calculate the probability. Okay. So here you are having ultimate range is minus infinity to infinity. So according to the condition, you will consider respective limits. Now here you are having the range like this, x1 to x2. Obviously the limits are within that range, x1 to x2. That's all. So when you have the probability density function, if you want to calculate the probabilities, you can use these formulas. Or if you are having probability distribution function, then if you want to calculate the probabilities, then you can use the function like this. Okay, so either from the probability distribution function you can calculate, or from the probability density function you can calculate. Okay, based on the given question, accordingly you can use respective formula. Okay, so next one is noise. So you will be having various noises like internal noise, external noise, etc. So for the time being, I am considering regarding thermal noise. What is the formula for power of thermal noise? Power of thermal noise. That means noise power only. Thermal noise. This noise is causing because of temperature. So P equal to KT into B. Where K is the Boltzmann constant and T is the temperature and B is the bandwidth. So which is same as bandwidth into N0. So here N0 is the power spectral density. Units are, see, this is the bandwidth. Bandwidth units you know. Units are hertz. And here left hand side you are having power. Power units are watt. So that means you are multiplying these two. From here you can guess watt per hertz. So when you multiply these two, hertz will get cancelled. You are getting power. So from these two, or from here, P equal to B into N0. From there you can write N0 equal to P by B. Or similarly here, P by B, you can write it as KT. Okay, so here N0 units are watt per hertz. So this thermal noise is also called as white noise. The other name of thermal noise is nothing but white noise. So here if you observe this noise power N0 is constant for all the frequencies. That's why since the noise power is equally distributed for all the frequencies, we are calling it as white noise. Okay. So regarding this power spectral density, so whenever you are drawing for one side, then its value is N0. This is the power spectral density of noise. Okay. If you are starting from 0 towards right hand side, positive frequency axis, then you are having N0. N0 is the constant value. It is distributed equally for all the frequencies. Okay. This is one-sided. Whenever you are drawing the power spectral density for one-sided, you can represent the white noise N0 value like this. Now, if you want to represent the same white noise for both the frequency axis, then can you guess what is the value we have to represent? If I want to represent for entire frequency axis, that means I am considering both negative and positive. So here in this case I am considering like this. It is constant only. Now can you guess, when I considered one-sided, I have considered N0. When I considered two-sided, now can you guess what is the value here I will consider? N0 by 2. So whenever you are having two-sided power spectral density, that time we will represent N0 by 2. If you are representing only for positive frequency side, N0. Okay. See, ideally speaking, we don't have negative frequency at all. But whenever you are drawing the diagrams, frequency spectrum, so for symmetrical purpose, we used to consider negative frequency axis. Okay. So whenever you are considering negative frequency axis, whatever the value you are having, you can make it half so that you can distribute. See, it is very simple logic. When you are considering only positive frequency, theoretically speaking, or not theoretically, for practical purposes, okay, we don't have negative frequency component, right? So we are having only positive frequencies. So for entire positive frequencies, if you are having N0, for symmetrical purpose, we are considering negative frequency axis. Okay, whenever you are drawing the diagrams, okay, for theoretical understanding purpose, okay, for symmetrical purpose, that time whatever the N0 value you are having, you make it half. And because here you are having whatever the positive frequency that you are having, so entirely another half you are having this side, right? So that's why you can make it half like that. Okay, so N0 by 2 for two-sided power spectral density, N0 for one-sided power spectral density. Okay, so this is the white noise. Its value is constant for all the frequencies. So this is the power spectral density. Okay, now if you apply inverse Fourier transform, then what you will get? This is the power spectral density you are having. That means frequency domain spectrum you are having. If you apply inverse Fourier transform, you will get time domain equation. Can you guess what it is? Yes, very good, Manoj. Very good. Yes, very good. It is the impulse function, right? Very good. So whenever you are having power spectral density, if you apply inverse Fourier transform, you will get autocorrelation function Rx of tau. Okay, since here you are having N0 by 2, it is a constant. Okay, so here you will get impulse signal delta of tau. Okay, So if you apply Laplace transform to this one, you will get power spectral density. Laplace transform of del of signal is nothing but 1. So that means you are getting n0 by 2. n0 by 2. Okay. Yes, very good. Very good, Manoj. n0 by 2 delta of tau. Delta of tau. Next one, noise through LTI systems. So for LTI system, if you want to know what is the output power spectral density, so which is nothing but input power spectral density, you have to multiply with h of f magnitude whole square. Magnitude of h of f whole square you have to multiply with input power spectral density. That will be the output power spectral density, right? Suppose you are having output power spectral density, but now if you want to know output power, what we can do, you are having output power spectral density, that one you can consider, and you can perform the integration with respect to frequency from minus infinity to infinity. See here, power spectral density is nothing but what? Power we have distributed among the frequencies, right? Now if you want to know the power, so you have to perform integration. Integration or area, both are same. So area of the power spectral density is nothing but power. Okay, right. Next one. So let us see few density functions. So first one is uniform density function. Uniform density function. So here on x-axis I am having from A to B, we are having the density function value as say k. So that means here from A to B the density function is constant. So that means here we are calling it as uniform density function. Uniform means its value. You can observe from A to B you are having density value as constant, right? So that means you can write this one as fx of x is equal to k for x lies between A and B. For x lies between A and B. Otherwise 0. Okay. Now if you want to calculate k value, you can apply the one of the property of probability density function. So we know one of the property as integral minus infinity to infinity fx of x dx is equal to 1. Okay, but here this particular probability density function exists from A to B only. That means towards left hand side up to A or towards right hand side from B. Okay, the probability density function value is 0. That means we have to consider only the integral limits from A to B. Okay, you can consider the integral limits from A to B. So in this interval fx of x is nothing but k into dx is nothing but 1. So here k is the constant, you can keep outside the integral. Integral dx is nothing but x. Here the limits are A to B. So that is equal to 1. So from here just substitute the limits. K into upper limit minus lower limit, that means b minus a is equal to 1. So from here you are getting k value as 1 by b minus a. K is nothing but 1 by b minus a. Okay, so by using the property of the probability density function, we are able to calculate the k value. But even if you observe, I have already mentioned this particular point. Whenever you are supposed to find the integration, integration is nothing but area under the curve. Integration is nothing but area under the curve. Now if you observe this probability density function, now all of you please respond, this probability density function is in which form, in which shape it is? All of you please respond. This probability density function is in which form or which shape? Is it rectangle or square, or is it triangle? Which shape it is? Yes, Mayank. Yeah, it is in the rectangular form. See, if you are continuing further, you can say it is a square wave, but here I have considered only one part, right? So it is a rectangle, right? So for rectangle, I hope all of you know how to find the area. How to find the area of the rectangle. Rectangle area is nothing but length into breadth, right? Length into breadth. Okay, so here length is nothing but b minus c into breadth or height. Here you are having k. So area under the rectangle, area of the rectangle is nothing but length into breadth. Okay, so according to the property, area under the curve fx of x or integral fx of x dx is equal to what? 1. So just equate this 1. So from here you will get k equal to 1 by b minus c. So either you are performing the integration after solving, okay, you will get the same answer. But if you want to, whenever in the question, if they give any particular fx of x waveform, okay, if you are having one of the constant, if you are supposed to calculate what is the constant value, okay, you can directly find the area under that particular curve. Okay, so suppose if you are having triangle, then half base into height. Okay, if you are having square, x square, if the length, if any of the side is having x units, like that. Okay, so accordingly, if you are able to calculate just area under the curve, okay, after that you equate to 1, from there you will get the answer quickly. Okay, so not only in this subject, whenever you are having, okay, either in signal system or network theory, okay, in any subject, whenever you are having one waveform, if you are supposed to find the integration, just observe the waveform shape, whether you are having triangle, rectangle, square, etc. Okay, or maybe the combination of those. Okay, so whenever you are supposed to find the integration, you will get the same answer. Okay, but if you want to get the answer easily, directly you can use area under the curve instead of performing integration. Okay, I hope it is clear for everyone. So here k is nothing but 1 by b minus c. 1 by b minus c. Next one, exponential density function. Exponential density function. So here it is starting from a, it is exponentially decaying, okay, as it is reaching infinite, right? So this one we can write mathematically like this: fx of x equal to a into e power minus bx, a into e power minus bx for 0 less than x less than infinity. That means starting from 0 towards infinite, you are having a into exponential decay, right? Otherwise it is 0. Otherwise it is 0. Okay, now here in this case we want to know what is the relation between a and b. Okay, so you can use same property. So integral minus infinity to infinity fx of x dx is equal to 1. Okay, so here from minus infinity to 0, you are having simply 0. But from 0 to infinity, you are having this value. So you can consider the integral limits starting from 0 to infinity. a into e power minus bx dx is equal to 1. So here a is the constant, you can keep a outside the integral. Then you can perform integral e power minus bx dx, which is nothing but e power minus bx divided by, regarding minus bx you will get minus b. Limits are 0 to infinity. Limits are 0 to infinity, which is equal to 1. Okay. So from here what you will get, I am writing minus a by b. Minus b I have taken outside, so I kept minus in the numerator. Minus a by b we are getting. Then just substitute upper limit first. E power minus infinity is nothing but 0 minus. Lower limit you can substitute. E power 0 is nothing but 1. So this entire value should be equal to 1. So here 0 minus 1 is nothing but minus 1. So minus into minus you will get plus. So that means a by b is equal to 1. So from here you are getting a equal to b. So you can substitute. In place of b you can just put a. That's all. Okay. So that means the given function is nothing but a into e power minus ax. Similarly, the next one is Laplacian density function. Here whatever the curve earlier you have seen, it will be symmetrical on with respect to y-axis. Okay, it will be on both sides. Okay. So here fx of x is equal to a into e power minus b mod x for x lies between minus infinity and infinity. Okay. So here also if you want to know the relation between a and b, you can use the same property. Integral minus infinity to infinity. That one I am splitting. From minus infinity to 0, I am considering. Okay. Then when you substitute this one, a into e power minus b. See, for minus infinity to 0, you are having negative values. When you are having negative values, mod x is nothing but minus x. Okay. Dx plus 0 to infinity. You are having positive values only. Right. A into e power minus b into x. That's all. Dx. So this overall two integration sum is equal to 1. Right. So here minus into minus is nothing but plus. Right. So a is the constant, we can keep outside the integral. E power bx dx is nothing but integral e power bx dx is nothing but e power bx divided by b. Limits are minus infinity to 0. Similarly, here a is the constant, you can keep outside. Integral e power minus bx dx is nothing but e power minus bx divided by minus b. Limits are 0 to infinity is equal to 1. So just substitute the limits. A by b I am keeping outside. Then e power 0 is nothing but 1 minus. When you substitute x value as minus infinity, e power minus infinity is nothing but 0 plus a into, okay, here minus b I am keeping outside, minus a by minus b into e power minus infinity is nothing but 0 minus e power 0 is nothing but 1 is equal to 1. Right. So here you will get a by b. Here this value is minus 1, minus minus will get cancelled. So that means you are getting a by b. So you are getting 2 times a by b is equal to 1. From here you are getting b equal to 2a, or you can write a equal to b by 2. Okay, so you can write in any version. Okay, so based on the given choices, whenever you are having any waveform, okay, if you want to find the relation between a and b, okay, you can use this property, and according to the waveform you have to split the integrals, and you can just perform the integration and do the calculation. After that, suppose for this question, if the question is MSQ, if you are supposed to identify the relation between a and b, okay, in one of the option if they give this one, you can choose, and in another option if they give, you can choose this one, because both are correct. Okay, so in this way, regarding probability density function, you will be having the waveform and you will be having some unknown value. Regarding that, they may ask the relation or they may ask the unknown value, like that. Okay, so based on the context, accordingly you can calculate the value or you can find the relation. Is it clear, Mayank and other students? So the next one is Gaussian density function. Yes, clear, very good. Next one is Gaussian density function. So here regarding Gaussian density function, you will be having the probability density function in the bell shape. In the bell shape you will be having. You will be having the probability density function in the bell shape. Yes, ma'am. If it is a white noise, means it is a constant only, n naught by 2. If you are considering all the frequencies, okay. Whenever Gaussian density is there, that is the bell shape. Okay. See here also, if you observe, it is symmetrical. Okay. Regarding the distribution, it was symmetrical. Okay, right. So regarding the probability density function, fx of x is equal to, see in this case the mean value is 0, because here if you observe here y-axis, okay, this waveform is symmetrical with respect to 0. Suppose if this waveform, if it is symmetrical with respect to some other y value, okay, that means that is the mean accordingly, right? But for this case it is symmetrical with respect to 0, like that. So for generalized case I am writing this density function. Okay, for this case if you are writing, you will get 1 by root 2 pi sigma square. For generalized case I am writing here 1 by root 2 pi sigma square into e power minus of x minus x bar whole square divided by 2 sigma square. Okay, but here in this case it is symmetrical with respect to 0, so that means mean value is 0. Sometimes in the question they will mention variance as 1, like that. Okay, so then this waveform, regarding this waveform, you will get 1 by root 2 pi into e power minus x square divided by 2, like that. Okay, for this case if you want to write fx of x is equal to 1 by root 2 pi into e power minus x square divided by 2. Okay, here mean is 0 and variance is 1. Mean is 0 and variance is 1. When mean is 0, variance is 1, you will get the formula like this. Okay, this is for generalized case. Now let us see the statistical averages. statistical averages. So the first one is mean value or average value, or all are same. Mean value or average value of a random variable. Mean value or average value of a random variable if you are supposed to calculate. The formula is expectation of x is equal to integral minus infinity to x into fx of x dx. Okay, whenever you are having the probability density function, if you are supposed to calculate the mean, which is nothing but integral minus infinity to x into fx of x dx. So this one, if you want in simple notation, you can represent this one as like m1. Okay, mean value 1. Okay, first order you are finding m1. Okay, so this one mean value or average value. So that means you are getting what? Whenever in your network theory, okay, whenever for a circuit, if you are having only the DC supply, because of that you will get, if you are calculating the power, you will get obviously DC power, right? So that means average value from here you will get, from here you are getting DC component, but if you are performing square of this one, you will get DC power. Okay, so for the timing you are getting DC component of the random variable. DC component of the random variable. This DC component value, if you are performing square, you will get DC power. Okay. Next one, mean square value. Mean square value. See here we have calculated just mean value. Okay, mean is nothing but expectation. Mean is nothing but expectation. But here we are performing mean value for what? One random variable x. But here we are performing for square of that random variable. That means expectation of x square. Expectation of x square, which is nothing but integral minus infinity to x square into fx of x dx. Okay, so from here you will get total power of the random signal. You will get total power of the random signal. Total power of the random signal. This one, if you want, you can label as M2. M2. Next, properties of mean. Properties of mean. See, whenever you are supposed to calculate the mean value of constant, so that is nothing but it is same. Expectation of constant is itself constant only. Suppose if you want to find expectation of some constant into variable, so constant you can keep outside. So k into expectation of x. K into expectation of x. Now suppose if you are having like this, random variable is there, constant is there. So for that, if you are supposed to calculate expectation, so you can perform individually expectation of x plus expectation of k. So whenever you are finding for a constant average value, it is same, right? So that means expectation of x plus k. Similarly, if you are having, if you want to perform expectation of x plus y, so that is nothing but expectation of x plus expectation of y. So in this way you can perform, you can apply these properties wherever required. Okay. And one more important point, whenever you are having probability density function is symmetrical with respect to y-axis any one point, then if you are supposed to calculate mean, see, you no need of using any pen and paper. Okay, what I am saying is, whenever you are having probability density function, if it is symmetrical with respect to some y-axis, okay, so then what you can do, just take the average, that's all. Okay, say for example, here you are having bell shape, so it is symmetrical about y equal to 0 axis, right? So that means, okay, so here, so according to this particular axis you are having the symmetrical, so that means here you are getting the mean value as 0. Okay, now with this understanding, tell me for this one, suppose this is the distribution density function you are having, fx of x. Okay, now for this particular function, if you are supposed to calculate the mean value, okay, later you can solve with the help of the standard formula just now I have discussed, you can try later, but now I have given the hint. Okay, in order to find the average value, whenever, now just observe this particular density function, you are having uniformly distributed from a to b. Now just take the average of these two. That is nothing but your mean value. That is nothing but a plus b by 2. Simple. A plus b by 2. Later you can try. Suppose this waveform only, suppose if it is lies between minus a to a. Okay, suppose if this waveform lies between minus a to a, then in that case what is the mean value? Instead of a to b, if it lies between minus a to a, then in that case what is the mean value? 0, right? Yes, very good ma'am, 0. Okay, because minus a plus a divided by 2 is nothing but 0, or the x-axis, this point is 0, right? So in that way you can calculate. It is very simple. Whenever probability density function is symmetrical with respect to one line, okay, with respect to y-axis line, whichever y-axis line it is symmetrical, that will be the mean value. Simple logic. Okay. Next one is variance. Next one is variance, that is nothing but sigma square, which is nothing but expectation of x minus x bar whole square. So just expand it, it is like a minus b whole square formula, a square plus b square minus 2ab. So just apply expectation for each and every term, you will get expectation of x square plus expectation of x bar square. So x bar square is a constant, I am keeping outside, directly I am writing. Next, here this is a constant I am keeping outside, then expectation of x is nothing but x bar. So from here you can write expectation of x square plus x bar square minus 2 times x bar square. So from here you will get expectation of x square minus x bar square. Okay, so this one you can write like this, expectation of x square minus x bar is nothing but expectation of x. So for this term you are performing square, right? So in simple words, what you can do, whenever you are supposed to find the variance is nothing but expectation of x square minus expectation of x whole square, or you can write expectation of x square is nothing but m2 minus expectation of x is nothing but m1, and you are having square. Now just tell me, m2 is nothing but what? Total power, and square of m1 is nothing but dc power. If you are subtracting dc power from the total power, now can you tell what is the resultant power? If you are subtracting dc power from total power, what is the resultant power you will get? Yes, very good Manoj, very good Mayank. Yes, see, obviously we are having two types of signals, one is DC, another one is AC, right? So previously I have mentioned, whenever you are having DC component, if you are performing square, that is nothing but it is giving DC power. And regarding M2 we have already mentioned, that is the total power of the signal. So if you are subtracting DC power from the total power, that is nothing but AC power of the random variable. Okay, so whenever you want to calculate the AC power of the random variable, that time you can calculate sigma square. So AC power is nothing but mean square. Mean square. See, previously also in the first chapter I have mentioned, whenever you are having the cos signal or sine signal, whenever you are supposed to calculate the power, okay, that time what you used to do, you used to calculate, suppose if it is voltage signal, Vrms square divided by R, okay. So you are performing Vrms square, okay. So for the timing consider R as 1, okay. So that means you are getting Vrms square, right. So Vrms, how you are getting? Vm by root 2. Vm by root 2. So for that you are performing square, right. So AC power is nothing but RMS square. RMS square. Okay. Actually the power is like, if it is voltage, Vrms square divided by R. If it is current, IRMS square into R. For the timing I have considered R value as 1. Okay. So RMS square you are getting. RMS is nothing but what? Root mean square. Root mean square. So square and root both will get cancelled. You will get mean square. You will get mean square. So that means AC power is nothing but mean square. Mean square. So similarly the last one, standard deviation. Standard deviation. Standard deviation is nothing but sigma, which is nothing but square root of variance. Just now we have calculated variance. For that, if you are performing square root, that is nothing but standard deviation. Okay. So just now we have mentioned that variance is nothing but mean square. For that we are performing root. Now can you guess what is this one? Root mean square is nothing but RMS. RMS, that's all. Okay. Root mean square is nothing but RMS. Suppose if you are having two random variables x and y, then you will be having joint probability density function. Joint probability density function, joint PDF. Fxy of x comma y. Joint probability density function. Fxy of x comma y. So regarding this, let us see the properties. So if you are having only one probability density function, suppose fx of x or fy of y, there we have discussed that integral over minus infinity infinity is equal to 1. Similarly here you are having two variables, so that means we have to consider double integral. We have to consider double integral. So if you perform integration over x and over y, so this overall value will get 1. Previously we have seen for one variable. Now when you are having two variables, there also it will applicable. Now next one, previously we have discussed for one random variable. Similar logic or similar analogy you can apply for two variables. Okay, right. Probability of x less than or equal to x1 and y less than or equal to y1. Then this is nothing but see, for the timing if you consider first integral is corresponding x, then just observe here you are having upper limit regarding x1, right. So that means it is starting from x1. Okay, sorry, this is the lower limit. This is the lower limit. Okay, right. So it is starting from x1 and upper limit is infinite. Okay, sorry. See, we have to calculate probability of x less than or equal to x1. So this is the upper limit. This is the upper limit. So that means you have to start the integration from minus infinity. You have to start the integration from minus infinity and upper limit is x1. So here the function is fxy of x comma y. So this is regarding dx, and similarly regarding dy, y limits, upper limit is y1, so that means lower limit is minus infinity. So in this way you can consider the integral limits. Okay, just like the previous case we have told. Okay, in the same way you can consider. Similarly the next one is marginal density functions. marginal density functions. So if you want to know only x regarding density function, but if you are having fxy, okay, so then you can perform integration over y. You can perform integration over y. Limits are minus infinity to infinity. See, when you are performing integration limits from minus infinity to infinity, whatever the y variable is there, that you are converting either in terms of x or you are converting into some constant. After that, rest of the function you are getting simply in the order of x only, right? So similarly, if you want to find fy of y, okay, so can you guess, in this case we will perform integration with respect to what? Previously we have performed integration with respect to y in order to get in terms of x. Now we will perform integration over which variable? You want to get y, right? So obviously how to perform over x, that's all. It is very simple. Okay. Suppose if x and y are independent, if x and y are independent, if x and y are independent random variables, then fxy of x comma y is equal to fx of x into fy of y. If these two are independent, then joint probability density function is same as if you are multiplying individual density functions, fx of x, fy of y. Okay, next one. If x and y are two random variables, if x and y are two random variables and z equal to x plus y, z equal to x plus y, then if you want to calculate fz of z is nothing but fx of x convolved with fy of y, fx of x convolved with fy of y. Suppose here I am considering x and y are two Gaussian random variables. If x and y are two Gaussian random variables having respective means mu1, mu2, having respective means mu1, mu2 we are having, and respective variance we are having like sigma 1 square, sigma 2 square. Okay, here also the same relation, z equal to x plus y, suppose. Then in this case fz of z, okay, for the timing I am not writing the density function, but if x and y are two Gaussian random variables, okay, so that means you are having probability density functions bell shape, right? So here we are performing x plus y, okay. So regarding probability density function, what you will get, you have to perform convolution among these two Gaussian density functions, right? So whenever you are performing convolution of two Gaussian density functions, you obviously will get Gaussian density function only, right? So that means z will be a Gaussian random variable, z will be a Gaussian random variable, but in that probability density function regarding mu will be mu1 plus mu2, and regarding variance sigma 1 square plus sigma 2 square. So just add the respective means and just add the respective variance. So this is about single variable and two variables, right? So previously we have seen regarding single variable expectation. Now similarly let us see regarding if you are having function like this, y equal to ax plus b, okay. Suppose if you want to find expectation of y, so just apply expectation on right hand side, you will get ax plus b. From here you can write a into a is a constant, you can keep outside, into expectation of x plus expectation of b, where b is the constant. So that means you will get a into expectation of x plus b. Okay. So similarly, if you want to perform expectation of y square, okay, just substitute in place of y ax plus b, So just apply a plus b format, a plus b whole square you are having, right? Or y1 plus y2 whole square format. So just write, expand it, expectation of a square x square plus b square plus 2ab into x. Okay. So here a square is the constant I am keeping outside, into expectation of x square plus b square is the constant. So expectation will be that constant only. Then 2ab is the constant into expectation of x. So in this way, if you are having the functions like this, you can apply expectation term in the same way. Okay. So you can apply like linear function, right? It is very simple. Whenever it is a constant, expectation will be that constant. Okay. Otherwise, according to the respective terms, you will get. That's all. Next one is random process. Up to now, we have discussed regarding random variables. Now, in the random process means you will be having in terms of variables and with respect to time also, right? So here you will be having two types of averages. One is ensemble average. Another one is time average. See, whatever the mean, variance, expectation of x square, okay, whatever the four expectations we have calculated, okay, all those we can apply here also. You can follow here, okay. So with respect to whatever the x is variable, so accordingly you will perform the integration with respect to x, okay. But only here time average means you will perform the integration limits with respect to the time. Suppose from t1 to t2 instant, if you want to find the corresponding expectation, you will consider the limits according. That's all. That is the only difference. Here in the ensemble average, just like the random variable, previously we have considered with respect to x or with respect to y, in the same way we will consider here. But whereas time average means we will consider the integral limits according to the respect to time. That's all, t1 to t2. If these two averages are equal, then that particular random process we will call it as ergodic random function. Okay, ergodic random process. If ensemble average and time average both are equal, then we will call it as ergodic random process. So here autocorrelation function we will represent Rx of tau, which is nothing but expectation of x of t into x of t plus tau. Expectation of x of t into x of t plus tau. Okay, right. So regarding the properties of autocorrelation function, let us see. See, if you are considering in the place of tau 0, in the place of tau just substitute 0, you will get expectation of x of t into, here tau I have considered 0, that means x of t. So which is nothing but expectation of x square. Now expectation of x square is nothing but what previously we already discussed regarding random variables. Similar logic here also you can apply, that is nothing but mean square value, ms. Square of the, you are performing mean for the square term, that's all. You are performing the mean or expectation for the square, right? So mean square value, or you can say total power, both are same. Next, Rx of tau, autocorrelation function. If you are applying Fourier transform, you will get power spectral density Sx of f. You will get power spectral density. Autocorrelation function and power spectral density are Fourier transform pair. Okay, this is the time domain equation. If you are applying Fourier transform, you are getting power spectral density. If you are applying inverse Laplace transform, you will get Rx of tau. Yes, very good, Mayank, very good. So Rx of tau is nothing but, or first you can write the power spectral density. You can write Sx of f is equal to integral minus infinity to infinity autocorrelation function Rx of tau into e power minus j 2 pi f tau d tau. Okay, so from here you can write Rx of tau as integral minus infinity to infinity Sx of f into e power, here you are having minus, here plus, that's all, e power j 2 pi f tau df. Okay, so I hope all of you know that omega equal to 2 pi f. Omega equal to 2 pi f. So just perform differentiation here. D omega equal to 2 pi into df. So if you want to write df, you can write d omega by 2 pi. D omega by 2 pi. Okay, so just substitute here. So when you substitute limits minus infinity infinity, accordingly, see here f limits are minus infinity, accordingly omega limits will be same, minus infinity to infinity Sx of omega into e power 2 pi f is nothing but omega tau. Here df is nothing but d omega by 2 pi. So that means here you will get 1 by 2 pi. That's all. Okay, I hope all of you studied regarding Fourier transform in your signals and system subject. Okay, so that's why for solving the questions of communication system subject or control system subject, okay, the basics of maths are important and even signals and system are important. Okay, most of the times wherever required, we will apply Fourier transform, Laplace transform, right? So those concepts are important. Once if you are learning the methodology, how to solve the questions with the help of Fourier transform, Laplace transform, inverse Laplace transform, inverse Fourier transform, you can solve the questions directly related to the maths if you are getting a question from the maths. Even if you are getting any question related to the application based questions, okay, based on those concepts in any of the core subjects, definitely those concepts you can apply. So once if you are able to learn those concepts, then you can apply so that you can solve any question related to the concepts based on those concepts, because all the core subjects based on the maths only, right? So once if you are strong on the maths, you can solve any question related to the core subject wherever. See, once if you know the concept, you can apply the concept, okay, for solving the question. But after that, whenever you want to solve, obviously you depend on the maths only. Okay, so it is very important if you want to score well in the coming GATE exam. So please thoroughly revise the maths. Okay, once if you are strong on the maths, then definitely you can attempt any question related to the core subject, provided if you are strong on the basics of those concepts. Okay, so here if you are having power spectral density, if you want to know the power, regarding that we already discussed. Okay, so just perform the integration of the power spectral density or area of the power spectral density, that is nothing but Rx of 0. Okay, so regarding this we already discussed earlier. So Rx of 0 is nothing but integral minus infinity to infinity Sx of f df. If you perform the integration of the power spectral density, you will get the power of the signal. Okay. Next one, stationary random process. So as the name implies, it is stationary. Okay, so whatever the time instants you are observing, so at those time instants, if the expectation is same or if the corresponding density functions are same, then we will say that it is stationary, right? Say for example, if you are considering one variable x and one time instant t1, if it is same as f of x comma t1 plus delta t. Okay, so at one instant you have observed, at another instant you have observed, if at both the instant if it is same, we can say it is a stationary. Okay, similarly if you are having two variables, you can consider x1 x2, similarly t1 t2, here x1 x2, t1 plus delta t, similarly t2 plus delta t, like that. Okay, next one is wide sense stationary, wide sense stationary random process. So regarding that, two conditions are there. So first one is expectation should be constant. Expectation should be constant. And the second one is Rx of tau. When you calculate the autocorrelation function, it should depend only on the value of tau, but not on the t1 or t2 like that. Okay. So it should depend only on the tau value. It should not depend on any other time instance. Okay, then we will say that particular random process wide sense stationary. So with this we have completed regarding fourth chapter, that is random process and noise. Okay, now the next chapter, that is chapter 5, digital communication. So regarding digital communication, see, in the analog communication what we are doing, whatever voice signal or any signal you are having, so yes Mayank, communication for EC branch the weightage is 8 to 12 marks. For instrumentation it will be 3 to 5 marks. Okay. So in the analog communication we have directly transmitted the analog signal, after the modulator we have transmitted. Whereas in the digital communication we will convert the analog signal into digital. We will convert analog into digital at the transmitter section. And at the receiver we will convert digital back into analog. We will convert digital back into analog. Because there are some advantages are there in digital, that's why we used to convert analog into digital. After that we used to transmit. At the receiver we will convert digital back into analog. Okay. So one of the main reason why we are converting analog into digital, the reason is noise. Noise effect is less in digital when compared to analog, right? So in order to convert analog into digital, first what we will do, we will consider the analog signal, and then with the help of sampler we will consider the samples. Okay, we will consider the samples. After that, with the help of quantizer, we will get whatever the samples you are getting, we will round figure those values to the finite values. Okay, after that, with the help of encoder, that means we are converting this value into the digital. Okay, right. Similarly, reverse process we will do there. Okay, so here whatever the analog signal you are having, while you are considering the samples, you should consider in such a way that at the receiver you should trace back or you should reconstruct the original analog signal, right? So for that sake, you should satisfy always one condition, that is called Nyquist criteria, Nyquist sampling rate. So that is nothing but 2 times maximum frequency of the signal. Okay, So always the sampling frequency should be greater than or equal to Nyquist rate. So if you are considering like this condition, then there is no issue in order to retrieve back the original signal at the receiver, right? Okay. So regarding quantizer, suppose if you are using n bit PCM, okay. So if you are having n bits, then you can have number of quantization levels as L equal to 2 power n. The relation between number of quantization levels and number of bits is like this, okay. If you are having, suppose 2 bits if you are having, you can have 4 levels. If you are having 3 bits, you can have 8 levels, like that, okay, right. So in this way, you can have number of quantization levels based on the number of bits. Hi Venki, good evening. Okay, so you will get the corresponding quantized value. After that, you will do the encoding. So here, suppose whatever the peak to peak value you are having, okay, so that one we are making into number of levels, right? So that means step size delta equal to peak to peak value divided by L, okay. So when you are having the range 0 to Vmax or minus Vmax to Vmax, like that, whatever the range you are having, that entire range you can consider maximum value to minus minimum value. From there you will get total value. Just divide that one with L. So from there you will get step size you will get. Now here you are getting one error, that is called quantization error, QE, because here you are having sample value something, but you are having something, but you are round figuring that one to some nearest value, right? So there is some difference, okay. So that difference is nothing but quantization error. Quantization error is nothing but sampled value minus quantized value. Sampled value minus quantized value. Sampled value minus quantized value. Okay. Now can you guess what is the maximum value of quantization error you will be having? Maximum error of quantization error. Yeah, Wajid, no issue. So for the time being, our class is going in English only. Okay. So you focus on the concept. Okay. So there won't be any language issue, but whatever possible you can try to follow. Okay. Right. QE max. See, here you will get the maximum quantization error, you will get delta by 2. Half of the step size, because it will vary from minus delta by 2 to plus delta by 2. Okay, right. QE max equal to delta by 2. Next, bit duration. Bit duration TB equal to the sampling time divided by the number of bits. If you take the reciprocal, then you will get bit rate. Bit rate is nothing but the reciprocal of bit duration. Reciprocal of bit duration, right? So 1 by TB, that is nothing but n by TS. N by TS. So reciprocal of time period is nothing but frequency, right? So n into Fs. N into Fs. So this is the bit rate. Bit rate equal to n into Fs. Okay. So here bit rate we are telling, that means units you will get bits per second or BPS. Bits per second. Okay. So from here you will get bandwidth also same. Bandwidth also same. But only the difference is units we will write in terms of hertz. That's all. Okay. Bandwidth bit rate of PCM. So this entire concept, whatever we have discussed, that is related to PCM. So in PCM, first we will do sampling, then quantizing, then encoding. So regarding this, all these formulas will applicable. Okay. Now if you observe, if you want to reduce the quantization error, then what we can do? We have to reduce the step size. we have to reduce the step size. If you want to reduce the step size, what you can do? You can increase the number of levels. You can increase the number of levels, right? Yes, correct, Mayank. RB is nothing but bit rate. Okay. So if you want to reduce the quantization error, you have to reduce the step size. Okay. If you want to reduce the step size, that means here denominator term, if you are increasing, then overall factor will get decreasing, right? So if you want to increase the denominator term, just observe here. If you want to increase the number of levels, that means the number of bits should increase, right? So this is the ultimate aim. Okay. If you want to get the minimum, if you want to get the quantization error minimum, right? So you have to increase the number of levels. That means you have to increase the number of bits. Okay. But if you are increasing the number of bits, then what will happen? Your bit rate is increasing and bandwidth also increasing. Okay. So that is the drawback. Okay. So whenever you are transmitting any signal, the signal bandwidth should be minimum as possible. But if you are using PCM, in order to reduce the quantization error, we have to increase the number of bits. Okay. That we can do. But if you are increasing the number of bits, the bandwidth of the signal also increasing. That is the drawback. Okay. Next one, regarding signal power. So for the timing, if you are considering the input signal as AM cos 2 pi FMT, right? So from there you will get AM square by 2. So regarding quantization noise power, you will get delta square by 12. So just take the ratio of these two. This is called signal to quantization noise ratio. Ratio of signal power and quantization noise power, that is nothing but signal to quantization noise ratio. So if you do the calculation, you will get 3 by 2 into 2 power 2n. 3 by 2 into 2 power 2n. So this is the normal value. Whenever they ask SQNR in the normal value, you can use this formula. But sometimes they will ask in the order of dB, decibels. SQNR in decibels. Okay, so that time what you have to do, you have to apply 10 logarithm of this entire value, 10 log SQNR. So if you do the calculation, after that you will get 1.8 plus 6n. Okay, you can remember this formula or you can remember this formula. Otherwise, you remember these formulas. Okay, after that you can substitute and derive. That's all. Okay, so 1.8 plus 6n. Here if you observe, the moment if you are increasing one bit, what is happening? Suppose if you are considering initially n value 0, then it is 1.8 only. N value 1, then 6 are adding. Okay, and if you are considering n value 2, 2 into 6 is adding. That means the moment if you are increasing one bit, then what is happening? 6 dB is increasing, right? So as you are increasing bit by bit, here regarding SQNR, it is increasing by 6 dB. Next one, electrical representation of binary data. So here we are having like on-off signaling, and next one is no return to 0 or non-return to 0 signaling. Third one is return to 0 signaling, and fourth one is differential encoding. Okay, so this on-off signaling we will use for amplitude shift keying, whereas non-return to 0 signaling we can use for pulse code modulation differential pulse code modulation, delta modulation, and frequency shift keying, phase shift keying. Next, return to zero signaling we will use in the fiber optic communication, whereas differential encoding, as the name implies, we will use this one in the DPSK, differential phase shift keying. Okay. Here on off signaling means we are keeping, okay, if the bit value 1, that indicates 5 volt or positive value. Okay. Bit value 0 means it is the 0 volt, like that. Here, whereas non-return 0 means bit value 1 means positive voltage, bit value 0 means bit value negative value means that is 0, like that. Okay. So similarly, return to 0, differential encoding, like that. Next one, DPCM, that is differential pulse code modulation. Differential pulse code modulation. Here in this case, we will reduce the quantization error. What we will do, as the name implies, differential pulse code modulation. Okay. Here we will perform the quantization. Okay. Here input to quantizer, in this case you will get the present sample minus previous sample. Present sample minus previous sample. So that means here in this case what we are doing, without increasing the number of bits, okay, we are able to reduce the quantization error. Okay. Because we are comparing the present sample with the previous sample. Whereas in the PCM, if you want to reduce the quantization error, we have to increase the number of bits. But here we are just comparing the present sample with the previous sample, and this difference we are considering. Okay. So here regarding bitrate and bandwidth, it is same as that of PCM. So for PCM, whatever the bit rate, whatever the bandwidth we got, it will be same formulas will applicable here also. Okay, next one is delta modulator. Delta modulator. See, it is a special case of DPCM. Okay, so just observe here. See, if you want to reduce the bit rate, okay, so here if you want, see, from the PCM, what is the drawback? If you want to reduce the quantization error, we have to increase the number of bits. But here the drawback, what we are getting bit rate and bandwidth more. That means as n increases, bit rate and bandwidth become more. But here we want to reduce these two. Okay. So if you want to reduce the bandwidth, you can reduce the sampling frequency or you can reduce the number of bits. But sampling frequency you cannot reduce up after some limit, because here the Nyquist criteria, if it is not satisfying, then you cannot reconstruct the original signal, right? So that is a drawback. So that's why we cannot reduce Fs after a certain limit. But regarding number of bits, we can reduce, right? So if you are considering the least value of n, that is 1, then that is nothing but delta modulator. So delta modulator is nothing but 1 bit DPCM. So here in this case, either the step size based on the comparison, either it may go plus delta or it may go minus delta. That's all. Okay. So here we are considering only 1 bit DPCM. That's all. So that means from here, bit rate is nothing but n by ts, where n we have considered 1. So 1 by ts is nothing but Fs. That's all. Similarly, bandwidth will remain same. It is Rb, same value Fs. here units are bits per second, here units are hertz. Now can you tell what type of errors we will get in delta modulation? Yes, very good Manoj, very good. See here in the delta modulator, okay, so here we will consider delta by Ts, okay, and dm of t by dt, dm of t by dt. So whatever the message signal you are having, okay, for that if you are performing differentiation, that is nothing but slope, and here step size is delta divided by Ts, okay. If these two are same, okay, you can consider modulus or magnitude, both are same. If these two are same, then there is no error. Suppose if you have considered delta value smaller, okay, if you have considered delta value smaller when compared to this one, okay, if you have considered delta value smaller when compared to this one, then you will get slope overload distortion. Okay, so that means you are supposed to consider more step size or optimum step size you are supposed to consider, but you have considered step size as smaller, okay. So because of that you are getting slope overload distortion. Similarly, if you consider opposite, so that means delta by Ts, if you have considered, suppose step size is more when compared to the magnitude of the slope, okay, so actually you are supposed to consider small step size, but if you are considering more than, okay, then you are getting granular noise. So you have to properly choose regarding this one in order to avoid these kind of noises. So this is about regarding baseband communication. Baseband communication means whatever the frequency spectrum you are having, that particular spectrum, it is having the information around zero frequency or low frequency, you can say. Okay. Now let us see regarding digital communication, band pass. Okay. So that means it will be centered around some other frequency. Instead of low frequency, it will centered around some other frequency. So regarding this, we are having IISc, so here I will write the headings: amplitude shift keying, then frequency shift keying, and then phase shift keying. So here IISc signal you can generate using balanced modulator or product modulator. Here also regarding, okay, I will consider this one as PSK and this one as FSK. Okay, so regarding IISc and PSK, with the help of balanced modulator or product modulator, we can generate these signals, whereas for FSK we can use VCO, just like FM signal. Okay, see, previously we have discussed like amplitude modulation, frequency modulation, phase modulation, their analog signal, but here we are considering the digital signals, that's all. Okay, carrier. So here bandwidth equal to 2 by TB or 1 by TB, you can write as RB, that is bit rate, Regarding PSK also same, bandwidth remains same, that is 2 by TB. Whereas FSK, you will get bandwidth as F1 minus F2 plus 2 by TB. See, whatever the bandwidth you are getting in ASK and PSK, you will get that one, but in addition to that, you are having F1 minus F2. Because here frequency shifting happening, so you have to consider the difference of these two. After that, you have to add this quantity. So that means among all, the bandwidth is more in FSK. Bandwidth is more in FSK. So regarding demodulator, we will use synchronous detector. In all the three cases, we will use same synchronous detector. Next, energy per bit, that is EB, which is nothing but AC square TB by 2. AC square TB by 2. So from here you will get AC value as square root of 2 EB by TB. Okay. So the same relations will applicable in PSK. AC square TB by 2, so which is nothing but square root of 2 times EB by TB, and same relation will applicable even here. AC square TB by 2, which is nothing but AC. AC is nothing but square root of 2 times EB by TB. Next, regarding probability of error. Regarding probability of error, P, which is equal to Q function square root of EB by 2N naught. EB by 2N naught. Next, so regarding PSK, probability of error is Q function square root of 2 times EB divided by N naught. 2 times EB by N naught. And for FSK, Q function square root of EB by N naught. EB by N naught. Okay, so these are the probability errors for ASK, PSK and FSK. Now let us rearrange all these functions into one standard form. So here I am having EB by 2N naught. Okay, so let us write all these quantities in the order of EB by 2N naught. Okay, so here I am having EB by 2N naught. So this one we can rearrange like this. So 2 times, okay, here EB by 2N naught I require. Okay, so that means in the denominator I require 2N naught. So I can multiply with 2. So then you will get 4 times EB by 2N naught. 4 times EB by 2N naught. Okay, next, here in the denominator I require 2 times N naught. So multiply and divide with 2. So 2 times EB by 2N naught. Now this is the Q function. So regarding Q function, there is one important relation. Q of x value will increase. Q of x value will increase as x value decreases. Q of x value will increase as x value decreases. Okay. So here if you observe, EB by 2N naught you are having. Okay, assume this is like x. Okay. Now when compared to this one, here it is becoming 4 times. It is becoming 4 times. Here it is becoming 2 times. Here it is becoming 2 times, right? So that means among all, okay. So So here EB by 2N0 you are having, then here 2 times, here 4 times. Okay. So regarding x value, initially you are having here, then next higher value is this one, next higher value is this one. Now when compared to this one, as x value increases, as x value decreases, q of value will increase. Okay. So with respect to that, okay, so here EB by 2N0 you are having, next 2 times, next 4 times. Okay. Otherwise you can consider like this. So among all, this is the 4 times you are having, then 2 times you are having, then 1 time you are having. That means you are decreasing x value. You are decreasing x value. Now if you are decreasing x value, then q of value will increase. Q of value will increase, right? So from this you will get, from this relation you will get probability of error minimum you will get in PSK. Probability of error minimum you will get in PSK. Okay. So that's why we will use PSK when compared to other two methods. When compared to other two methods, we will use PSK. See here regarding FSK, you are getting more bandwidth. Because of that, we will avoid FSK. Okay. So regarding ASK, among all, you are getting more error you are getting here. Okay. So that's why we will, when compared to all these methods, among all, PSK is the recommended one. Okay. And here if you observe, in all the 3 cases we are using synchronous detector. So whenever you are using synchronous detector, there is the possibility of quadrature null effect. Okay. If you want to eliminate quadrature null effect, then we will use DPSK. If you are using DPSK, then there is no quadrature null effect. So obviously, see here we have discussed regarding ASK, PSK, FSK, that is for binary. Binary. That means we have considered 2 symbols. When you are going for higher number of symbols, obviously from the 2 symbols when you have observed, among all the 3, PSK is the better when compared to other 2, right? So obviously when you go for higher order number of bits or number of symbols, okay, then obviously we will recommend PSK only, right? So accordingly you will get M-array signaling. So for the timing, if you consider regarding PSK, M-array PSK. Okay. So the bandwidth formula is this one. Bandwidth equal to 2 times RB divided by log m base 2. 2 times RB divided by log m base 2. Suppose if you consider m value 2, log 2 base 2 is 1, you are getting 2 times RB. You are getting 2 times RB. Yes or no? That is nothing but 2 times RB, PSK, right? So in this way, suppose if you are considering m value 4, accordingly log 4 base 2 is nothing but 2, 2 will get cancelled, bandwidth is nothing but RB. Okay, right. If rectangular pulses are replaced with raised cosine, if you are having, then in that case, in order to calculate the bandwidth, the formula is RB into 1 plus alpha, divided by log m base 2. So log m base 2 denominator is same, RB also same. Okay, but here you are having 2, but here the rolling factor, whenever you are having alpha rolling factor, so you have to multiply with 1 plus alpha. Okay, so in this way you can calculate the bandwidth regarding any number of symbols. If you are having, in order to find this formula you can use. And regarding raised cosine, so this is the bandwidth formula. I hope all of you know that the relation between information and the probability, that is inversely proportional. If the probability is more, then information is less. If the probability is less, then you're having high information, right? So mathematically, in order to remove this particular proportionality, in order to replace some constant, we will represent like this: I equal to logarithm of 1 by p base 2. 1 by p base 2. Here units are bits. Okay. Suppose if probability is 1, then you don't have any information, right? When you substitute here, 1 by 1 is nothing but 1, log 1 is nothing but 0. Okay. But if you are having probability is 0, that means you are having high information. Okay. Very high information you are having. Next one, entropy. Entropy is nothing but the average information. Entropy is nothing but the average information. So when you're having number of symbols, okay, so you just multiply the probability with logarithm of 1 by probability and add all of them. That is nothing but entropy. Entropy is nothing but H is equal to summation over I probability into log 1 by probability. Probability into log 1 by probability base 2. So just add all of them. Okay. Then from there you will get entropy. Units you will get bits per symbol. Bits per symbol you will get. So in general, whatever the symbols you are having, for all those symbols, if you are fixing the number of bits, okay, for each symbol, if you are fixing the number of bits, then we will call it as fixed length coding. But based on the probability, if you are assigning the number of bits differently based on the probability, then accordingly you will get in that coding the number of bits for each probability will vary. So accordingly we will call it as variable length coding. Okay. For each symbol, if you are giving uniform number of bits, suppose if you are giving 3 bits for each symbol irrespective of the probability, okay, then we will call it as fixed length. But suppose, see, just if you observe this relation, if you are having probability high, then less information. If probability is less, then more information is there, right? So that means based on the probability, so whichever symbol is getting more chances in order to appear, so that particular symbol, if you are able to represent with the less number of bits, and whatever the symbol, if it is having less probability, okay, for that symbol if you are representing more number of bits, so because of that you can effectively utilize the number of overall code. Okay, so that is the advantage if you are going for variable length coding. Okay, so regarding variable length coding, we are having 2 types. One is Shannon-Fano coding and other one is Huffman coding. Shannon-Fano coding and Huffman coding. So in these 2 codings, we will arrange the symbols in such a way that the probabilities are descending order. That means highest probability symbol we will keep on the top, then next probability symbol, like that. The last symbol which is having the least probability, like that we will arrange. But here in the Shannon-Fano coding, okay, for each iteration we will arrange the symbols in such a way that whatever the equiprobable symbols we are having, okay, so we will keep, suppose first half we are keeping 0, next half of the symbols we will keep 1, like that we will continue the process. Okay, whereas in Huffman coding we will keep the like that only order, but after that we will just add, by adding which probabilities we are getting equal probable. Okay, like that we will continue up to the last stage. Okay, from there we will give whichever is getting highest probability. For that we will start assigning the symbols from last stage to the first stage, right? So 0 1 0 1, like that. Okay, So in this way, what is happening? For the symbol which is getting high probability, it is having less number of bits when compared to the symbol which is having least probability. Okay, so because of that, among these two, this coding is the efficient one, because when you calculate the entropy, here you will get less number of bits when compared to this one. Okay. So regarding information rate, if you want to calculate information rate, see, it is very simple. Information rate or bit rate. Here units you will get, units are bits per second. Okay, units are bits per second. Now just observe, entropy we got the units as bits per symbol. Now we want bits per second. So what we have to do, we have to multiply two quantities in such a way that one quantity is bits per symbol, and other quantity is symbols per second. Then what will happen? Symbols will get cancelled. Then you are getting bits per second, right? So bits per symbol is nothing but entropy. H. Okay, and symbols per second is nothing but symbol rate. Okay, symbols per second is nothing but symbol rate. So if you multiply these two, from there you are getting information rate. It is very simple. Okay, right. So maximum entropy, if you want to know, maximum entropy. Maximum entropy is nothing but H max, which is nothing but log m base 2. Units are bits per symbol. So the next one is channel capacity. C equal to B into log 1 plus S by N base 2. So by using Shannon-Hartley law. Okay, so if you know the bandwidth, if you know the signal to noise ratio, by using this formula, you can calculate the channel capacity. So here you will get the units as bits per second. So with this we have completed the last chapter. So in this particular session we have discussed regarding communication system subject. We started with the analog communication, regarding amplitude modulation, then DSB-SC, SSB-SC, VSB-SC. After that we have discussed regarding angle modulation. There we have discussed regarding frequency modulation and phase modulation. Okay. After that we have discussed regarding AM and FM receivers. We are having tuned radio frequency and then super heterodyne. And then we have discussed the formulas related to those two concepts. And then we have discussed regarding figure of merit. After that we have discussed regarding random process and noise. There we have discussed regarding random variables, how to calculate the various expectation values, expectation of x, expectation of x square, variance, mean square, etc. Right? And then we have discussed regarding probability density function, regarding probability distribution function, properties, etc. And for various density functions, we calculated the relation between A and B, or relation of A or relation of K, etc. We have discussed. And then we have discussed regarding digital communication, PCM, DPCM, DM. And similarly, we have discussed regarding ASK, PSK, FSK. So all those formulas are important, whatever we have discussed in this entire session, even regarding information theory. All the formulas you can revise once. Okay, if you are unable to remember any formula, just you can practice. Okay, so by practicing you can remember. Okay, so you will get most of the questions in the communication system subject. You will get the questions based on these formulas, but sometimes the question seems to be lengthy, but read the question with patience, then definitely you can understand what is the given data and what you are supposed to calculate. Once if you are able to understand the concept, once if you are able to understand the question, then definitely whatever the formulas you are having, you can apply. Okay, so for easy understanding regarding probability density function, we have considered few functions. In the question, in the GATE exam, they can give any other function, then definitely you can substitute according to the respective function. That's all. Okay. Yes, Mayank, no issue. Whatever we have discussed regarding formulas, okay, just apply those formulas. With the help of that, you can solve. Okay. Okay, since you're having less time, just focus whatever the concepts you have learned till now. Okay, those who not attended earlier regarding our GATE score booster session, so please watch regarding digital circuit subject and communication session subject in your free time, and regarding quick revision session also. So if you are able to go through these videos regarding digital circuits and communication, whatever the questions we have discussed which are important with respect to your coming GATE exam, and whatever the formulas we have discussed in these sessions, okay, so if you are able to revise all these concepts and all these formulas, okay, and that is more than sufficient. Okay, so definitely I hope you might have got the confidence by this time. Okay, even if you are unable to, no issue at all, just go through these videos and practice once, definitely you will get the confidence. Okay, so with this confidence, go and attempt your coming GATE exam. So definitely you all can score very good rank. Okay, yes, thank you everyone for attending these sessions. So in the next week, I think in the coming days, on 31st January and February 1st, we are having regarding maths and general aptitude also. Okay, so Priyanka ma'am will take those sessions, so please watch those sessions, so that from maths and GA together you will get around 25 to 27 marks, right? So it is very important. Okay, so if you are able to score maximum from maths and GA, obviously you can enhance your score while attempting the core subjects, right? So that is the very important. So please try to attend those sessions also, upcoming sessions. So regarding the notification, you can see in the regarding the timetable, you can see in the description. Okay, so all of you kindly subscribe our channel and click on the bell icon, so that whenever you are getting any upcoming video, you will get the notification, so that you can attend the respective session. You will get maximum benefit from the session. Okay, so if you are from any other branch, okay, so regarding the upcoming schedules, you can see in the description link. Okay, so accordingly you can watch the respective sessions. Okay, thank you everyone for attending this session. Thanks a lot. So I am stopping here. Thank you everyone.